Kindly unmute yourself, ma'am.
Gerald sir, shall we start?
Okay, ma'am.
John?
Yeah.
Yes. Winston sir, we are starting.
Go ahead.
Okay.
Thank you, sir. Very good afternoon to one and all present here in this Zoom room. Thank you very much for joining us again in the afternoon session. Today we have two speakers for this afternoon. I invite Dr. Gerald Anthony to introduce the speaker of third session, Dr. John Mcendraj.
Thank you, ma'am. Can you hear me?
Yes, yes.
Yeah. Good afternoon to all. It is really delightful to introduce our guest speaker, Dr. John Mcendraj from University of Beirut, Germany. He pursued his UG and PG at St. Joseph's College, Turkey. He completed his PhD in chemical science from University of Bologna, Italy. He had been trained through summer research fellowships jointly organized by Indian Academy of Science and National Institute for Interdisciplinary Science and Technology, NIIST Trivandrum. He had also obtained junior research fellowship jointly funded by CSIR and IIT Chennai. He was also a part of European Union FP7 IT and Fine Lumen project of ISOF and CNR Bologna, Italy. He had an internship on perovskite solar cells in University of Tor Vergata, Rome, Italy. He completed his postdoc at University of Trieste in Trieste, Italy. He is currently pursuing his postdoc at University of Beirut, Germany. His area of interest are organic charge carriers, photovoltaics, photo-induced charge transport process, transition and inner transition metal complexes, electron energy transfer processes, carbon nanomaterials, supramolecular assemblies. His area of interest transcends the border of various fields of sciences. His research interests indicate that he is one of the vanguard of versatile chemical science field. He is also skillful in XPS, UPS characterization of organic, inorganic, pristine and doped samples and electrical characterization of photovoltaic devices. He has hands-on training on operating SEM, AFM, steady state and time resolved absorption and fluorescence spectroscopy. And also he has the ability to handle the linearly polarized normal infrared spectroscopy and microspectroscopy. He published more than 20 papers in peer-reviewed international journals. He presented papers on various occasions at Boston, USA, France, and Italy. His achievements and publications portray his cognizant and acumen triads in photochemistry, nanomaterials, solar cells, supramolecules, and other allied research fields. Due to time constraint, I am unable to divulge more details about Dr. Mcendraj. It is a great honor for us to welcome such an eminent and erudite personality for today's webinar. On behalf of Chemistry Department of St. Xavier's College, Palayam Kotai, I welcome you, Dr. John Mcendraj, to deliver your speech. Thank you, sir. Now the session is over to Dr. John Mcendraj.
Thank you so much, Gerald sir. Actually, I'm blushing. Maybe I could just start my presentation right away then. Yeah. So someone needs to confirm me whether you're able to see my slides. Hi, is everybody there?
Okay. John, you're okay.
Okay, cool. Let's go. So thank you so much once again, Gerald sir, for making such a good introduction on me. And actually, as I said, I was blushing because it's really hard to hear when you actually are in a group and when somebody is praising you. Anyway, so for today's talk, I have chosen a topic in which actually I'm presently working on, and the topic is actually doped organic hole conductors. Actually, it's a bit different from the topic title that I have given already. So instead of doped hole conductors, I've added this organic part additionally in here. And today we'll be talking more in general terms rather than going into the details of it. So I would give a general perspective of the impact and relevance of this doped hole conductors in present day technologies. You would come across, or you would see some slides in which I have shown some examples that are relevant in our day-to-day life, and almost everybody, one of us, are using a few of the devices in which we already have organic hole conductors. Okay, there is some lines are going on. Okay, cool. So generally, everybody actually presents this acknowledgement slide at the end of the presentation, but I want to start with acknowledgement because without these people, I would not be presenting the same here at the present situation. So I take this opportunity to present, to thank my professor, Mukundan Telekat, and also my university, University of Bayreuth, in which I'm working right now. And because of them, actually, I'm exploring different avenues of the science right now. And partly Siemens, because they were the one who actually funded the project in which I'm going to talk, I mean, the one that I'm going to discuss today. And also the other local projects, or the local government projects, which are known as like Soltech and SFP, which are actually paying my salary, let's say. And apart from these main players, like I also thank all my teachers from my school until my college. And particularly, I would like to express my gratitude towards Professor N. Xavier. We fondly call him as NX, and Professor Professor S.R. Beater, and Professor Madhyalagan from St. Joseph's College. So these three were actually motivating me towards more in the direction of research. And I'm pretty much sure it's like without them, like I wouldn't be even stepping out of my college. And in addition, I thank the patrons and conveners of St. Xavier's College for giving me such a great opportunity. It's my privilege actually to take part in such a good webinar, and I see that like quite a number of students are getting in. So once again, of course, I thank Dr. Baby Mariatra for inviting me for such an event. And on the other hand, like I thank all the audience who actually step into the seminar, and even at around 4 o'clock. I mean, it's really hard even to do afternoon classes in the regular days, but now in this corona situation, I hope everybody is doing good, and then everybody is stepping in at around 4 o'clock. That's a great thing. So I thank you all for that. And in addition, actually, it's my privilege to take part in this one, this webinar, especially organized by St. Xavier's, because present head of chemistry department, basically Professor Selvakumar, was my first teacher during my college days, like during my bachelor's. Here, I fondly getting this nostalgia there. So thank you so much once again for you. So with all these thanks, I get into the topic. So maybe if you're seeing everybody's like I'm continuously getting some information around. Is it okay? Or yeah. Anyway, so the topic that I would like to talk on today is organic electronics. So you probably everybody might have heard something in our in day-to-day life, like electronics or electricals and things like that. So this is a new term, which is organic electronics, and have just taken a definition for this, like how far this is different from the regular electronics, or what it consists of. So this is one of the biggest upgrowing fields in the recent times. So this field actually consists of preparing molecules, basically synthesizing organic molecules, particularly conjugated systems, like pi orbital one after another, so that like the electron is more delocalized over the entire structure of the system. And of course, synthesis, and then characterization of this particular molecules or polymers in principle, because polymers is one of the system in which you have a huge pi localization or pi delocalization over at least more than a nanometer or a few nanometer scale, which actually show desirable electronic properties such as conductivity, and eventually you could use them in place of regular or conventional inorganic electronic material, such as silicon-based electronics or germanium-based electronics and things like that. So the question is like, why organic? The point is like, why a new material or a new system or a new field, whereas like we already have enough of electronic systems like all around us. Technology is taking over, and one of the important factor that actually beats the technology is the growth of the electronics, I would sadly say. On the other hand, this is, as Nai was asking the question of what is the point of coexisting of Rajni and Kamal Hassan at the same point of time in the movie era, at the same era in the movies, let's say. So actually, I took this comparison because I know that's like it's kind of happy thing to see film stars in scientific presentations. On the other hand, they portray different characters, and I think this is going to be important for my talk. The one thing is that's like when you consider Rajnikant or when you compare Rajnikant and Kamal Hassan, both are kind of two extremes. Like one is highly focusing on commercial movies, and another one is highly focusing on acting-oriented things, and still both of them produce successful movies. Same thing is what's going to happen, or you would realize at the end of the presentation probably. It's like we are talking about a technological applications. So the end product is more or less the same, but you use different materials with different intrinsic properties. So what are the properties and why it is so? That's what actually I'm going to show in next few slides. So for example, in the case of conventional systems, here I have taken liberty to consider the examples of silicon-based and metal oxide-based conventional electronic systems. So, sorry, and somebody is scribbling on my screen, it seems like. Anyway, so the point here.
John, I think you can go ahead. Otherwise, you can do one thing. You can annotate your presentation, or you can just go ahead. Some people, they may use mobile phones, touch phones. So when they touch the screen, it appears here.
Okay. I was kind of wondering, like, if somebody wants to say anything or something.
No.
Which I never came across. That's why. Anyway.
Okay.
Yeah. So the point here is that's like I would like to make a direct comparison between conventional electronic system that we have already in our hands and then organic electronic system that is about to come to our hands or already partially we have. So what are the advantages or what are the disadvantages or let's say pros and cons of this particular field? So when we talk about conventional system, which is actually on the left side of the balance, where you could see that's like they actually show excellent electronic properties. And in fact, that's the main reason why we are sticking with these materials until now, because if you consider supercomputers or gadgets, it's probably you have it right moment at this moment at your hands, like all made of silicon-based technologies or silicon-based electronics, let's say. And they are processed through solid state. You have to grow crystals, and then you have to process the crystal, and you have to do everything in the solid state. So like there is no solution-based processing involved with that. Conventional systems, they are heavy in weight, basically. That's another reason why your mobile phones are slightly heavy and your computers are heavy. Like partly, it is the case. And almost all of them are rigid. So because all of these inorganic systems are mostly crystalline, so they are quite rigid. So if you bend it or flex it or conform it, like basically it would lose their electronic properties. So you may not get them back. So this is actually another point that you all might have realized at one point of your time, like in your life, like when you drop your mobile phone to the ground, like the screen cracks and then it hardly works, or it doesn't work as it was before, because the connection between the broken pieces are lost, and so that like nothing works again. On the other hand, on the right side, if you see then, so like the properties of the novel materials based on organic electronics. In this case, the electronic properties are not up to the mark of the conventional systems, but however, they are not quite poor too, because over the time, people put a lot of effort to make it actually look better and even competing with this existing technological systems or technological properties. And then the good points compared to the conventional systems are actually the organic material based electronics or devices are solution processable. Basically, you can dissolve them in solvents and then you can spin coat them, or you can inkjet print them and evaporate them. So you have actually a possibility for doing or processing your material in very different way. It's like basically versatile way. The possibilities are endless. And second important factor is quite lightweight. So consider that like nowadays every man is or every human in this earth is actually taken along with him or her considerable amount of electronic gadgets. So if you are keep on sticking with this conventional systems, probably maybe in 10 years we may have to carry at least 5 kilos of electronic gadgets with different batteries and electronic systems along with that. But like the point of moving towards more in the direction of electronics is having it in lightweight without compromising the properties of them. At the same time, you wanted to have it as a flexible system. Like as I mentioned before, so here you cannot bend your screen. For example, when you consider charging your phone or batteries, for example, so you cannot bend any of them. But if you prepare the same devices or materials, you can actually bend them, conform it around, and this is kind of quite important when it comes down to bioelectronic applications in the near future. So the important point is that like based on all these advantages, like organic electronics actually marching forward day by day. So the three important pillars that actually constitute or let's say help to grow this organic electronics field is organic light emitting diodes and organic photovoltaics and organic field effect transistors. And I'll, instead of going deep into this device structures or device science, I rather show their applications, and maybe then you could easily understand like where this organic electronics come into play in your day-to-day life. I would like to start with organic light emitting diodes actually. So Samsung company is one of the largest cell phone producing company with a semiconductor technology in their hand. At the same time, they are the one who actually first introduced OLED based phone mirrors or smartphone screens. And this is where exactly you would see how easy it was and how good the organic electronics was helping Samsung to actually produce the entire screens with very low cost. At the same time, the resolution is quite higher compared to the conventional silicon-based technologies or inorganic LED-based technologies. So, and also, as I mentioned in my previous slides, like they also introduced a flexible or foldable phones, and this is only possible because of the organic systems like they involved in preparing this screens. If it was like based on inorganic LEDs, then basically it won't work after one time. And when it comes down to organic photovoltaics, so we already have a lot of photovoltaic technology in the market, especially silicon photovoltaic technology is one of the unrivaled technology until now, which is actually producing a good amount of renewable energy and adding more amount of current to the grid every day. But when it comes down to home applications or in-home applications, such as having solar cells on your table where you just have ambient light and then you still want to produce electricity out of this ambient light. At the same time, when you have shaded windows where you have windows which is actually based or focusing outside where the sunlight comes in, and then you still want to harvest all those sun energy into electrical energy, which you could use later on. So this is one step further in that direction, because organic photovoltaics helps to produce devices or solar cells that actually can be used in such in-home applications. And more importantly, you could actually prepare them in any versatile designs in which you want, actually. Also, you could hang it around anywhere with their limited amount of efficiency. So the efficiency is not comparable with silicon technology, but the application is aimed at different parts of the houses, because as long as you have seen, the silicon-based technologies, solar cells are actually only you could find on the rooftop. But on the other hand, like these kind of new technologies can come into your house and still produce energy that could be used for our day-to-day applications. The third part is organic field effective transistors or field effect transistors. This is one of the very fast growing technology, because with this you could actually produce a printable CMOS logic circuit. CMOS logic circuit is like metal oxide semiconductor based logic circuits. So that was conventionally prepared with metal oxide semiconductors, and now you can go and print these logic circuits just by programming on the computer with choosing the right material. You can print it on top of any substrate that you have. So this would have a direct implications in foldable screens in the future. So this is one of the examples. You could, I mean, people who are interested could go into Wiki and then can have a better look at it, because this is going to be one of the viable technology in the near future. So after all explaining this, like I would like to take time to thank these three gentlemen here who actually won Nobel Prize for developing the concept of organic electronics from 1960s onwards. So Professor Alan Heger, Professor McDermott, and Professor Shirakawa. So according to them, it's like basically the idea is to develop organic materials which actually could conduct when they are actually connected with alternating single and double bonds between the carbon atoms. And most of their study was focused on polymers, because it was in a way easy to produce highly conjugated system that too, as I mentioned before, for a longer distance. So in that case, you end up in a system, or you end up having a polymer that actually have a highly conjugated backbone, in which the electron can be transported from one end to another end, and it means basically the system can be conducting. And on the other hand, there are some cases where you have very poor conductivity of this polymer or this organic material. There, basically, we come up with the idea of doping. So here I stop and emphasize on this particular point, that is actually doping. So this is what I'm going to talk or explain a little more in detail in coming slides. But before getting into that part, I would like to take a detour and then show you a little more, or let's say refresh your fundamentals on physics about semiconductors. So all what you'll be seeing for the next few slides contains the basics of semiconductors that you probably have studied in your schools or in the early bachelors. So semiconductors as such, like all this theory is developed based on inorganic materials. Here I'm also explaining it for the inorganic materials, but then slowly I would explain what or how it would look like for organic materials. So this is important in order to understand the concept of doping and also the concept of conductivity in terms of electronic or charge carrier transport in organic materials. So as I said, so here we have like band structures. For example, if you consider a regular semiconductor, so we have a valence band and a conduction band. Think about silicon or think about germanium or all known semiconducting material that you probably have studied in your classes. So there is an energy gap between a conduction band and a valence band. That is what we call like band gap. So that is called EG, like band gap, as we might have studied. And the band gap is one that actually defines in this conventional systems whether a material is a semiconductor or a conductor or an insulator. So here you could directly see that, like when you have no band gap at all, basically when in a material where the valence band and conduction band actually mix together, and the electrons located in valence electron can freely pop into conduction band and roam around, which basically contribute to the conductivity of the system, then such materials we call them as conductor. When the band gap is quite large, there is no possibility of promoting an electron to the conduction band and make it to contribute to the conductivity of the system, then those materials are known as insulator, because no matter what happens, like an electron is not going to the conduction band here. So for example, glasses in here, like no matter how hard you try, you would not be able to make it conducting. So this is very day-to-day life example that we probably see. On the other hand, when it comes to semiconductor, or we call it half conductor. So this half conductor means basically either it could conduct or not conduct. So the point is, if you are able to make it conduct, like I would explain that in the next slide, but basically here the band gap is comparatively smaller than the band gap of the insulator and slightly bigger than, or comparatively bigger than, the band gap of the conductor. So depends on the condition, depends on the environment, depends on the stimuli from external. This material can conduct or cannot conduct, or either can conduct or cannot conduct. So what are those stimuli? If you see that, like you could use light as an external stimuli or heat. So which one you could use, or what wavelength you want to use or have to use, or what amount of energy you're supposed to pump in to make an electron to go to the conduction band, all depends on the band gap of the system. So this is basically the intrinsic property of a material, the semiconductor that we are talking about. So here I would like to give an explanation, or let's say the naming of the system. So what is hole and what is electron? This is I think much more important to understand the coming slides. If you're not understanding holes, then there is no point of talking about hole conductors. So focus here. We had electrons here, so you apply external stimuli. So you basically apply some light, let's say sunlight, and heat, and consider the semiconductor as a silicon semiconductor, normal silicon plate. So upon getting this external stimuli, a few electrons from the valence band actually got pumped into conduction band. Now these electrons are quite free, so that like they can contribute to the overall conductivity of the system. And that's how we call it a semiconductor, like a half conductor. Now, if you remember the previous slide, the amount of electrons which are actually located in the conduction band is not as high as the conductors, or example, metals, where you have plenty of electrons, pool of electrons which contribute to the conductivity of the system. That's why the conductivity of metals, or let's say copper wire or gold wire, is quite high and comparable with this organic semiconductor system, where only few electrons take part in the conductivity of, or electronic properties, in defining electronic properties of the system. So the electrons, which you probably already know, were located in valence band, and once it is gained energy, it goes to the conduction band, and then of course it's known as electron. But when it leaves a positive hole or a positive charge in the valence band, and that's what we actually call or name as holes. So we are going to talk about or see systems in which hole is being conducted, or the materials which are actually good for hole conducting in different devices. And on the other hand, so have to see like how to improve the conductivity of such a conventional systems or conventional semiconductor. So you can actually go for doping. So that's quite common in the field of silicon. So here I have given examples for those. So when you talk about intrinsic semiconductor, as I said, like there is no electron in the conduction band or no hole in the valence band. So like everything is as normal. But when you actually introduce a donor to the system, in which the donor has an excessive electron, and that electron actually being donated to the entire matrix, now you have some additional electrons in the conduction band that is not coming from the silicon as such, but from the donor. So in this way, you create additional charges in the conduction band, additional electrons, and these electrons can contribute to the overall conductivity of the system. So this is what we call actually N-doping, and such systems are known as N-type materials. So why N? Here, N stands for normal. So normal type material in the sense like the conducting mechanism is actually happening through electron transport. So electron transport is the normal mechanism or the known mechanism, established mechanism in which the metals actually conduct electricity. So that's the reason why this is known as N-type material. On the other hand, when you go with an acceptor material which removes an electron from the matrix, or for example, in this case, silicon and boron. So when an acceptor accepts an electron from silicon, it leaves only holes in the valence band. So in this case, this material no longer can conduct predominantly the electrons, but they can conduct holes because those are the major carriers at the valence band level. So actually, I have to mention here about the Fermi level, which probably it's too much right now for you. On the other hand, the Fermi level is actually decides like which material can act as what, whether N-type or P-type. For example, in P-type material, you see that like basically your Fermi level is pretty close to the valence band. On the other hand, N-type material, the Fermi level is pretty close to the conduction band. And yeah, basically that is it. And yeah, as an example for P-type doping and N-type doping, I've chosen the regular conventional system, which is actually silicon and boron, where boron has only 3 electrons in its electronic configuration, and when they form covalent bond with silicon, they always leave out a positive charge. So you have like excessive amount of positive charge in your system. On the other hand, with phosphorus, you have 5 electrons in the outer shell, and when it forms a covalent bonds with silicon, you would end up in having an additional electron in the system. So you basically have an excessive amount of electrons. So this system would behave in a normal way. So this is N-type material, and here is a P-type material. So how does it look like when it comes to organics, like organic molecules? So here we no longer have bands, but defined orbitals. So I leave the question to you, like why in inorganic we have bands, and with organic materials we have defined orbitals. Please look into Wikipedia, or you can write me later. Anyway, so here we have defined orbitals in which electrons are residing. So we call these orbitals as a Homo, Homo -1, and Homo -2, and so on. In the same way, the unoccupied orbitals are known as lowest unoccupied molecular orbitals. So we have LUMO, LUMO +1, and LUMO +2, and so on. So very similar to the inorganic systems, you go with a donor which actually donates an electron. So you add a new electron to the LUMO of the system. So you have 1 electron residing. So as soon as the LUMO receives an electron, the energy of the orbital decreases, and it goes below the Fermi level of the system. So now you have excess amount of electron in the system, so that like it can behave as N-type material, and this process is known as N-type doping. On the other hand, you go with an acceptor, a material or a system or a molecule which can accept an electron from the matrix. In this way, you actually create a positive charge in the HOMO. So as soon as you create a positive charge, basically the energy of your HOMO would go little bit higher in energy, and then it shifts more close to the Fermi level of the system. In this way, you actually have created more amount of holes in the system so that the material would behave as a p-type material. And to explain it in a practical sense, here this is nothing but an oxidation of your system. And in the case of n-type doping, it's nothing but reduction of your system. So this is a straightforward process, but in terms of in electronics, it is known as n-type and p-type doping, respectively. So I have chosen a system with two different examples. So we have zinc phthalocyanine. There's an organic molecule which has a HOMO and LUMO line here. So basically, you need a redox couple which could either oxidize or reduce the zinc phthalocyanine. If you're oxidizing the zinc phthalocyanine, basically you are p-doping the zinc phthalocyanine. If you are reducing the zinc phthalocyanine, then you are n-doping the system. So if you want to have a reduction, basically you need to come up with a system which has a higher lying HOMO. That is what you are seeing here. So we have like ruthenium bisterpyridine as a ruthenium complex, basically, which has a higher lying HOMO, and then LUMO, which is empty. So the donor, however, has the energy comparable with the LUMO of the zinc phthalocyanine. So now there is a possibility for the electron to transfer from the HOMO to LUMO, even in the ground state, like without doing any other thing. Like you just take a material and take a zinc phthalocyanine, mix them together in solution, and then you get this. Like you can basically reduce zinc phthalocyanine with ruthenium bisterpyridine. On the other hand, one of the famous dopant system, which is F40CNQ, which is very highly electronegative in nature. So it has like very low lying LUMO in the sense like the LUMO energy of the system is quite lower compared to many other organic systems. Since the LUMO energy value is quite low, or the orbital is lying quite low, even lower than the HOMO of the zinc phthalocyanine. Now, when you take a zinc phthalocyanine and F40CNQ in a cuvette or in a beaker and just add a solvent to that and just mix them together, now an electron would transfer from the HOMO of the zinc phthalocyanine to the F40CNQ LUMO. So in this way, so you p-dope your zinc phthalocyanine, and with F40CNQ you n-dope. With F40CNQ you p-dope, and with ruthenium bisterpyridine you n-dope your zinc phthalocyanine. The important parameter here is the matching orbitals. So no matter what you want to do, whether you want to n-dope or want to p-dope, as long as you have good orbitals with similar energy levels of your LUMO or HOMO according to what you want to do, then you can be actually successful in doping your material. So what I'm going to do with this, so where do I commence? Like until now we have seen the basics. So what we would do with this, so this is where actually I'm working on. So this is one of the famous hole conducting material intrinsically. So intrinsic hole conducting material in the sense, without even doping, it has some amount of positive charges in the system because of the defects in the system. So we finally call spirometad, and we have this system, and we wanted to dope the system. So we wanted to dope efficiently with as low amount of dopant possible, so that like we could use the system for any applications. So while we were wondering like what dopant we could use, we also characterized the spirometad. So this is nothing but a spectroelectrochemical graph, which is this is a 2D contour of the spectrum. On the other hand, like if I deconvolute this, basically this is an absorption spectrum. So I just took an absorption spectrum, a UV visible absorption of the solution of spirometad in a cuvette, where I put 2 electrodes and then I start applying potential. So basically, I electrochemically oxidize spiro to see what are the features of the oxidized species that I could get in this spiro solution. So for example, if you see at the beginning, like without applying any potential, at 0 potential, the spiro has no other feature throughout the entire wavelength region except the ones that are corresponding to the neutral molecule. So it has a band at around 300 nanometer. So you would see in the next slides the normal 2D spectrum of a spirometad. But anyway, here with increasing potential, when you go up to around 1.2 volt, you start to see a new feature, which is coming at around 520 nanometer. At the same time, some peaks around, some broad peaks around 1200 nanometers. So these peaks probably correspond to the oxidized species of the spiral, or oxidized spiral species. On the other hand, when you go higher and higher in potential, then you prepare or you produce a new molecule or a new system, which actually absorbs something around 650 nanometer as well as about 900 nanometer. And we also checked whether this process is reversible, because the point is you're oxidizing with positive potential. So the system should come back to its original position when you reduce them back to 0 potential, because there is no driving force for the system to stay in the same oxidation state. So we went down from 2 volt down to 0 volt again. So you could see, like when we drift back from 2 volt to around 1.2 volt, so we again start to see the new features that we saw before around 520 nanometer in here. At the same time, the intensity of these features actually start to decrease. And concomitantly, we see also the generation of new features that we saw before. So basically, we are just playing here with potential. So we oxidized and then reduced, then you can actually keep on doing as many times that you wish. But the important take-home message from this experiment is that, like, when you oxidize a system, you see a new species at around 520. When you highly oxidize a system, then you see a new species which absorbs at around 700 nanometer, also at around 900 nanometer. So keep it in mind, because it's going to help you in the next slides. We also actually, while we were looking for the dopant, we received a copper complex from Siemens at that time. So the copper complex is actually known as copper trifluoromethyl sulfonamide, and in short, we say copper TFSI. So we wanted to see whether the copper TFSI could actually dope our spiro or not. For that, we need to know the redox potential of copper TFSI, as I mentioned in a couple of slides before. So we did cyclic voltammetry. It's a very fundamental experiment, and we calculated the potential, or let's say the LUMO level of the copper TFSI, which, as we calculated, lies at around minus 5.3 electron volt. And here is copper TFSI LUMO. And we did the same for spirometad to understand where the home of the spiro actually is located. So in that case, we found that the spiro is located around minus 4.9 electron volt. Of course, this is in negative, so minus 4.9 lies a little higher than minus 5.3. So now you see that, like, a HOMO is lying higher than the LUMO of our copper TFSI system. In this case, there is a possibility for an electron transfer from HOMO to LUMO very easily, because we have a driving force of about 400 milli-electron volt. Like, the higher the driving force you have, the driving force in the sense, higher the difference between the HOMO of your matrix and LUMO of your dopant, the better the oxidation process would happen, or higher would be the yield of the oxidation process, we put it in that way. And now we started to see whether it is really oxidizing or not. So here, as I said, like, theoretically, we knew that's like there is a possibility because we have 400 millielectron volt of driving force, but we wanted to see practically whether mixing copper TFSA and spiro produces oxidized species. So what we did is we carried out UV visible absorption titration experiment. So in this experiment, we took a spiro solution in a cuvette, and then we started adding little amounts of copper TFSA to the system. So while we keep on increasing the dopant concentration, we start to see new features at around 520 nanometer, which you could see much better in here. So this is how, sorry, on the other hand, like this is how a pure spiro would look like without any feature in here, which now you can correlate with the spectroelectrochemistry data. But anyway, with increasing dopant concentration, or let's say copper TFSA concentration in spiro-emitted solution, you start to see new peak that is actually increasing in intensity with respect to the copper TFSA concentration. And the important factor here is that like even with 1 mole%, like you could see the red curve, so 1 mole% of copper TFSA, we are able to see the new peak in the spiro absorption. So now if you compare the spectroelectrochemistry and the peaks that we obtain here, that I would show in the next slides. So we see the new feature around something around 520 nanometer, which clearly tells that like there is a redox chemistry is going on between copper TFSA and spirometad. So here what where we compare. So you can clearly see that like the black curve and red curve and green curves are from spectroelectrochemistry. So with increasing potential, so while we apply more and more potential, basically we electrochemically oxidize the system. Now we compare these curves with chemically oxidized systems. So we took copper TFSI and we added to spiro, and then we compare those spectra with the one from spectroelectrochemistry, the dotted lines here. So those are quite well matching with the electrochemically oxidized species. So now with confidence, we can say that like copper TFSA has oxidized spirometad. It means that basically we are now able to p-dope spirometad with copper TFSI. And what next? So we found that like, yeah, we can actually dope spiro, but is it of any use? Whether the system can find any applications in or has any technological relevance. So in that case, in all the technological applications, we need to prepare films. Unfortunately, the system that we actually prepared, that is itself spirometad and copper TFSA, was not actually producing neat films. So in order to go for a device or an application, the first important parameter is to have clean, uniform film without any holes or any aggregation on surface of the substrate. But it was not the case. So we just took spiro, copper TFSA, mixed them and spun on a glass or an ITO, and we found such strange figures in here. So because of this reason, we moved on to evaporation technique, where we actually used different sources to evaporate these materials. And the important point is it's not just evaporation, this is called co-evaporation. So basically, you evaporate both spirometad and our copper salt together at the same time with matching appropriate concentration. But we should be in control of the copper salt because we don't want to put more amount of copper salt in our spiro. Anyway, the benefit of moving from solution process to evaporation process was really helpful for us. On the other hand, it has its own intrinsic benefits, such as like you could produce very uniform pinhole free films at the same time, no matter how rough your surface could be. Like through evaporation, you could conformally cover your surface, and we are adding no additives or no solvent is needed for this. And very importantly, you can control the concentration of the dopant, which is in our case the copper salt, in a very accurate way by using a few sensors around. And we can also control the thickness, and this technology can be easily upscalable to different devices or different applications, because evaporation is a basic method that people use in industries for preparation of screens and many other technologically relevant applications. And with this, so what we can do now, so like, oh, sorry, before that, like, yeah, I wanted to show a clean, highly uniform film that was prepared by co-evaporating spiral and copper salt in this machine. So once the films were prepared, we tested also for the oxidation process of spiro in films also, because like initially we had the idea before, like, okay, you take two materials and add in solvent. There, the solvent plays a vital role in stabilizing the oxidized species, and also they help to interact with each other. But when you go for co-evaporation, we are not certain whether this chemical reaction can happen in gas phase, because this reaction should occur while they are moving from the source towards the substrate. So again, we carried out UV-vis absorption experiment, and we found very similar peak as the solution-based titration experiments, a new peak at around 520 nanometer. This once again confirms that even in solid state, our dopant is able to p-dope or positively dope the spirometal. The important factor is that, once again, the conductivity of the system. So the goal, or let's say the idea of doping itself is coming from here. It's like how much you are improving your conductivity by doping, or you're gaining or you're losing, or what is happening. So in our case, we characterized our material. So without any dopant in our system, we calculated about 10⁻⁷ Siemens per centimeter as conductivity of the pristine spiro material without any dopant. But by adding merely 2 mole% of dopant or copper TFSI to our system, we improved the conductivity to 10⁻⁴ Siemens per centimeter. On the other hand, the relative increase in conductivity is actually 3 orders of magnitude with just 2 mole%. On the other hand, with a further increase up to 6 mole%, of course, we went up to 10⁻³ Siemens per centimeter, on the with a relative increase of more than 4 orders of magnitude. When we go beyond 6 mole%, the conductivity didn't actually go further increase. I mean, it's like it started to stabilize at this point. We call this point as a saturation point. So the electronic properties or the conductivity got saturated at this point with this much amount of, let's say, 6 mole% of copper TFSA in it. Fine. So we got a good film which is showing good conductivity upon doping. So what we can do with that? That was the bigger next question for us. So here I wanted to show this famous NREL plot we call. NREL stands for National Institute for Renewable Energy Resources. So National Institute for Renewable Energy Laboratories, basically. So if you go to the web page, or if you follow this link, you could see such an efficiency plot for all the solar cells that is being produced in this world in present day, starting from 1975. So this is basically like a checkpoint for all the solar cell technologies. So people prepare the devices and then send them to this NREL, and then they would evaluate how efficient the device is. So since this plot is quite crowded, I've just taken a piece of it and exaggerated in here. So follow me through my laser pointer here. The yellow dots with red lines is actually corresponding to the perovskite solar cell devices, which I would explain in the next slide. So this is actually very recent technology, which started around 2013, and then it went up to 25.2% of efficiency in just less than 7 years of time. On the other hand, just right above here, this blue square, which is actually 26.1 value, which is nothing but the long researched, quite conventional single crystalline silicon-based technology. So the point that here I would like to mention is that's like with this perovskite solar cell technology, we are pretty much close and comparable with the long existing silicon-based technology. So this was one of the biggest driving force for the field to put a lot of efforts in promoting or to improve the overall device efficiency of the perovskite devices. So we thought, okay, like we could prepare perovskite solar cells. So what is perovskite solar cells on the other hand? Perovskite is a type of material. It's basically the crystal structure of a type of materials. Like in this case, it is basically lead iodide with methylammonium cation in it. So it's a crystal material with methylammonium and lead iodide mixed together. Further details, definitely it takes another 1 hour or something on this material, but please Google perovskite solar cells, that you would find a hell amount of material to read for. Anyway, so this is one of the devices. And then if you actually look closely from the energetic point of view and also the materials involved in such devices, this we call NIP perovskite solar cells. NIP solar cells means like basically N-type material you have on one side. Here we have titanium as N-type material, and perovskite, methylammonium lead iodide, which is basically an intrinsic semiconductor. And then you have a P-type material at the other end of your system, where we have a spirometad as a whole conducting material, or let's say P-type material. And then these layers were sandwiched between FTO and gold. Those are electrodes. So when you shine light, or when you place this device open air or in light, basically the methylammonium lead iodide, the perovskite, would absorb light and then produce charges like free carriers, we call them, and they produce electrons and holes. The produced electrons would travel towards the electrode through N-type material. And in fact, that's the reason why we have an N-type material next to perovskite in this case. On the other hand, the so produced holes would travel through spirometad and would eventually reach gold electrode. So now you see that like upon shining light onto a device, you made free charge carriers, and you made these carriers to move around. So this is how you get electricity, or you produce electricity from solar cells. This is a fundamental principle of the solar cells. But anyway, the important function of the spirometad and titania are basically you have to control the movement of these charge carriers, the positive holes and electrons, negative electrons. So the electrons should not go in the other direction, as well as the positive holes should not go towards FTO, because in this way there won't be any current, and then there would be a big recombination between electrons and holes. So the idea is that like you keep them apart as much as possible, and then before they recombine, you transport them towards the electrodes. So as you can clearly see that like here we have a spirometad as being used as a whole transport layer in these systems. So we thought of like, why don't we just use this system for our with our dopes, whole conductors. So the bigger problem, despite the fact that you have seen it shows about 25.2% efficiency, the bigger problem for such a device family is the reproducibility and stability. So here we thought like why the reproducibility and stability are created, I mean like come in as big issues in the case of perovskite solar cells. There could be like intrinsic and extrinsic factors, and one of the major contributing factor is actually a whole transport material, because in these regular devices, spirometad is still doped with lithium TFSI, is another inorganic salt. You need to add this salt to spirometad so as to p-dope it, so that you can improve the conductivity of the system. The problem is the amount of lithium TFSA added to the system is more than 50 mole percentage, basically. So you have like in 1:1 ratio of lithium TFSA and spirometad. So more amount of dopant than the spiro as such. And the other important factor here is that like the lithium TFSA is not a direct redox couple for spirometad. It basically helps with the oxygen. So like basically it helps the spirometad to react with atmospheric oxygen and then get oxidized naturally. So there is no control of oxidation process over the time. And so there is no reproducibility for the device performance. And on the other hand, as I said, spirometad is an organic molecule, as we have seen before. And lithium TFSA is a salt. When you mix these two systems, basically a polar and a non-polar systems, or ionic and a non-polar system together, basically they phase separate. Since they phase separate, the film quality will be very, very poor. So basically we end up in having like non-homogeneous or inhomogeneous films with a lot of holes in it. So all these things could cause, or they are causing issues with the device performance over the time. And these are the ones actually causes the problem for reproducibility and also the stability. So that's why we thought, like, why don't we go with our co-evaporated copper TFSA doped spirometad as a whole transport layer. So in this case, I'm just going to show the results that we obtained, the end results of our devices. So this is a device configuration. So we took FTO as one of the electrode, and then similar to the slide that I showed before, titania as the N-type material, and PCBA is the derivative of fullerene as an interfacial layer, and then perovskite, methyl ammonium lead bromide, and then spirometad doped with copper TFSI, and then finally another electrode that is gold on top of it. So with increasing dopant concentration, we actually obtained very good efficiency, something close to 12.5% in average. So the point is, like, no matter whether you are increasing the conductivity of your system with increasing dopant concentration, still the device efficiency remains almost the same, or at least it is not disturbed by the increased dopant concentration in our case. And also you could see that, like, device performance is not quite scattered throughout the system. Like, we could obtain highly reliable, highly reproducible devices one after another in different batches. And here again, the batch to batch reproducibility of the system. So we prepared one set of batches with 2 mole percentage of copper TFSA doped spiro, and prepared devices and characterized them. In a similar way, another batch, another day, another sample, 2 mole percentage of copper TFSI, spirometad, and prepared the devices. And then we compared the end results of these, or let's say the performance of these devices. So in all our cases, with increasing dopant concentration, in all our cases, between batches, like, we are able to reproduce the results. So this is one of the important achievements from our side, that, like, we are able to produce reproducibly devices with decent efficiency. It's not that, like, we come up with a layer and that kills entire device efficiency, but we are able to show something very decent from our side. And another important factor is the stability. Here we store the devices and we measured the device performance over the time. So here I normalized the device efficiency to 100, and then I monitored the device efficiency over the time, basically. So at least in our case, with our copper TFSI doped spirometad, we could say clearly that, like, at least over 200 days, the devices were not losing more than, or not losing or going down to 85% or even below at least 10 to 200 days. So the bigger issues were reproducibility and stability. So with our new doped systems, we were able to achieve device performance with better reproducibility as well as better stability. So here I would like to summarize. So today in this talk, I tried to explain what is organic electronics. Also have shown few examples of doping organic semiconductors, or why we need to dope organic semiconductors. And then I showed our personal work, which is actually copper TFSA doped spirometad, and also explained how we characterized with UV visible absorption spectroscopy technique. So also introduce another new processing technique, which is a cooperation strategy, which could be very useful for industrial applications. And the important factors are the impact of doping on our organic material, where we found more than 4 orders of increase in the conductivity of spirometad compared to its pristine form. And finally, we achieved perovskite solar cells with device maximum efficiency about 13.5%. They are importantly reproducible, as well as we achieve better device performance even with very little amount of dopant in our system. Also, the devices that we produced are more than 200 days stable in this case. So with this note, I would be happy to answer any of your questions if you have any. Thank you.
Thank you, Dr. John. It's been a very energetic presentation, and we are receiving feedback. Like, it's very informative and it is very educative to people who are not working in this field.
Glad to hear.
Yeah, thanks a lot. Thanks a lot, John. And one participant has raised a question like, can we predict these characteristics of these conductors or organic conductors using Gaussian?
Sorry, using Gaussian?
Gaussian.
You mean the program?
Yeah.
Gaussian program?
Yeah.
Well, actually speaking, it's much easier than going to do such Gaussian calculation and all, like, because you take a material and you measure the conductivity and then you get it right immediately, whether your doping works or your material is conducting or not. This you would know in a matter of seconds. But of course, you can do Gaussians, but doing Gaussian in the sense, like, it's not straightforward because at least until now, there is no program that could predict exactly the energy gap. So as long as you know the transfer gap between your conduction band and valence band correctly, then you can predict whether the material could be as insulator or a semiconductor or a conductor in principle. It is possible, but definitely we don't need to go for such sophisticated systems, while you can do it in a matter of minutes.
Participants, if you have any other queries, you can raise your hands and I will unmute you. You can ask Dr. John.
Okay, it seems that
people are appreciating you. Fantastic presentations are very informative. Okay, a person called James Gerald Parimalam asked a question: if this organic conductor can be reduced to a solar size, I don't understand what he's trying to ask.
Maybe if I get the question correctly, so is it possible to build a solar cell as such, like organic solar cells?
That's the thing. Yeah, maybe we can ask him to talk. I think he's the one, the father of our student. He's working in a polytechnic college. Maybe we can ask him to interact with you. I will unmute him.
Sure.
Sir, Dr. James Gerald, sir. Please, you can unmute your system and you can talk to Dr. John. If you want, you can talk to John in Tamil.
Yes, sir. I'm asking. So, good evening, sir.
Oh, good evening, sir. Yeah, please. Yeah, go on. I'm hearing.
So, whether this organic conductor reduce the solar cells size area?
Yeah. Solar cell, I mean, I'm not getting the question clearly. So you wanted to reduce the size of this to prepare a solar cell or something?
John, can we go by Tamil?
Yeah, sure. I mean, nallave Tamil pesla.
The solar, நம்ம இப்போ solar conductor யூஸ் பண்றோம்ல சார்?
Yeah.
இப்போ அந்த solar cellsலாம் வந்து இப்போ அந்த number of cells increase பண்ணும்போது நம்ம conduction வந்து increase ஆகுது. இப்போ இந்த கண்டக்டர் யூஸ் பண்ணும்போது இந்த சோலார் சைஸ் ஏரியா வந்து ரெடியூஸ் பண்ணலாமான்னு கேட்கேன்.
ஓகே, ஸோ நீங்க இப்ப இருக்கிற டெக்னாலஜி, அதாவது நம்ம இப்ப வெளியில் நீங்க பாக்குற இந்த சோலார் செல்ல அதை பத்தியும் பிளஸ் இந்த டெக்னாலஜி பத்தியும் கேக்குறீங்க இல்லையா?
ஆமா 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 ஆமா.
ஓகே, ரெண்டு வேறு எக்ஸ்ட்ரீம் அப்படின்னு சொல்லலாம். என்னன்னா, இப்ப மார்க்கெட்ல இருக்கு, அதாவது நீங்க இப்ப வெளியில பாக்குற டெக்னாலஜி வந்து சிலிக்கன் பேஸ்ட் டெக்னாலஜி. அதுக்கான எஃபிஷியன்சி, அதுக்கான இன்ஸ்டலேஷன் ப்ரொசீஜர் எல்லாமே ரொம்ப டிஃப்ரெண்ட்.
ஓகே ஓகே
அப்படியே நீங்க இங்க ஆர்கானிக் மெட்டீரியல்ஸ் பத்தி கம்பேர் பண்ணீங்கன்னா இதோட எஃபிஷியன்சி இதோட அப்ளிகேஷன்ஸ் எல்லாமே டிஃப்ரெண்ட்.
ஓகே
ரெண்டையும் 1 to 1 ஃபர்ஸ்ட் ஆஃப் ஆல் நம்மளால கம்பேர் பண்றது இப்ப இருக்க சுச்சுவேஷனுக்கு ஒத்து வராது. ஏன்னா இன்னமும் எஃபிஷியன்சி ஆஃப் தி சோலார் செல், ஐ மீன் ஆர்கானிக் சோலார் செல்லோட எஃபிஷியன்சி வந்து இன்னும் இம்ப்ரூவ் ஆகிக்கிட்டே இருக்கு டே பை டே. பட் ஸ்டில் அது வந்து இன்னும் கம்ப்ளீட் பண்ணல. ஸோ அதுக்கு பதிலாக இதை யூஸ் பண்ணா பெட்டரா இருக்குமான்னா கண்டிப்பா இப்ப இருக்க சுச்சுவேஷனுக்கு இருக்காது. மேபி இன்னொரு 10 yearsல டெக்னாலஜி பெட்டர் ஆகலாம்.
ஓகே, தேங்க்யூ சார். தேங்க்யூ
யா
சார்.
தேங்க்யூ ஃபார் த கொஸ்டின்.
தேங்க்யூ மேடம்.
Thank you, sir. Thank you. He's the father of our student. He's working in a polytechnic college, and we are very happy to know that you are participating here, sir.
Thank you, madam.
Next, Dr. Sir, kindly you can mute your system. Next, we have Dr. Anto-Arigiraj to ask you something.
Yes, please, ma'am.
Hello, good evening, sir.
Good evening. Stop calling me a sir because I'm still a student, as I said before. I mean, it's like I'm just studying right now.
No problem, sir. No problem. Since perovskite type of crystals are very much interested in the field of organic solid state chemistry, may I know what are the significance of it?
Yes, actually, the direction in which we are looking at this material, I mean, is it okay to tell it in English or you want to switch it to Tamil or something?
Whatever.
Okay, so okay, so the perovskite as such, like we are looking to answer the question in the direction of solar cells only, like and the field is pretty much actually hot right now because people are trying to produce also quantum dots for light emitting applications and very other different applications, like even memoristors and for even qubit applications we are trying to look into this perovskite now. So the point is this has a very specific structure, crystal structure, so that like even with this inorganic, basically this is an organic inorganic hybrid. So you come with methylammonium salt, like methylammonium organic salt, and then you mix it with a lead iodide, which is inorganic by nature. So you mix these things together to produce a system. I mean, like if you look in maybe a Wikipedia, like you could easily type and have a look at it. Like the crystal structure is like quite fuzzy. It's quite intrigued to see that. Like, and because of the crystal structure, basically the conduction band and the valence band actually come pretty closer and has a band gap of 1.7 eV. So it's like perfect for photovoltaic applications.
So the doping may be easy. So we are expecting the doping may be easy in it. Am I right?
For the moment, people are not doing doping of perovskite as such because the application is different. Because this is a hybrid system where we wanted to use in solar cells, so where we could use other doped systems to transport the charges. But we need some material which actually could produce charges, like absorb light and produce charges. Like in the case of silicon, for example, you have intrinsic silicon which actually absorbs light and then produce charges. And then you have N-type silicon and then P-type silicon which can transport these charges to respective electrodes. So we want a material here. I mean, we use this perovskite as an absorbing material, not as transporting layer here.
Okay, thank you. Thank you.
Yeah, thank you.
Dr. John, there is a question from a participant.
Yeah, please.
Lifetime of these cells are very limited. How to increase it?
Well, this is $1 million question right now because everybody is looking for the same answer. Now, actually, if you see the performance, the efficiency of the devices, which is actually already competing with silicon technology. So in principle, if we are just considering the efficiency, this product should be already in the market. But still, we didn't see any products related with perovskite devices or perovskite solar cells in the market, just because of the same issues that I have mentioned before, the stability and reproducibility. So people now trying to use a combination of materials to prepare this perovskite layer so that like they can improve the intrinsic photo instability issues with perovskites. And also they are modifying this next layers like charge transport layers. Actually, as I explained in my slides, like that's one of the reasons why we actually jumped into this field, because we thought like maybe we could change the doped whole transport layer in the system, and then that may help to improve the overall stability of the system. of the devices at the same time without compromising the efficiency. This is what we try to address in that case. Like, and what we found was that, like, if you are adding less and less amount of dopant, maybe that actually helps to improve the overall stability of the system. So many groups are working throughout the world to understand different parameters involved or different processes involved in these devices. And now the time has improved from 200 hours to 2000 hours. So they are getting slowly stable over the time. So even one startup company started this task to produce stable devices. Who knows, maybe in 3 years, we may get the product out in the market.
Okay. Dr. Stephen is having a question. Dr. Stephen, you can unmute yourself. Dr. Stephen, you can unmute yourself and you can be connected with, please be connected with Dr. John. Okay, I will read out his question.
Yes.
Which method is adopted to increase the efficiency of solar cells?
Okay, so if it comes again to perovskite devices, basically now they are improving, they are working on each layers, as you said, like N-type material, P-type material, as well as the perovskite as such, because there's a huge molecular engineering is going on to prepare stable as well as efficient perovskite devices, and also to prepare them in a defect-free conditions. Like the biggest point, or let's say advantage of perovskite devices is that, like, you can prepare this polycrystalline system through solution processing. At the same time, this is the biggest disadvantage too, because, like, when you come up with the solution processing, you actually end up in having more defects in the system. So more the defects, lesser the charges would be transported to the electrodes. So the idea is you produce more amount of free charge carriers, like positive holes and electrons. At the same time, you have like very good conducting layers. Like now they actually replace titanium with tin oxide, which is slightly better than titanium and also quite stable. They can also transport much quickly, let's say faster, the electrons from perovskite towards FUO. And also people are synthesizing pretty many organic materials now in the direction of addressing the same question, to improve the efficiency as well as improving the overall stability by improving the overall conductivity of the charge transport layers. So it's not like one system, like you improve this perovskite layer so that like you gain better efficiency. It's kind of a multi-layer system. So you have to work on each layer to improve the overall efficiency of the system. There is no choice.
Okay, there is another question. What are the factors affecting the stability of perovskite solar cells?
One is intrinsic problem of the perovskite as such, because it has a poor photostability. So you just take the material and shine light on it, then maybe after 2 hours, in presence of moisture and in presence of oxygen, the material is decomposed already. So the material decomposed to lead iodide and methyl ammonium. Basically, this methyl ammonium iodide would evaporate from your substrate. So this is the biggest problem right now, and yeah, people are working on it now.
Okay, there is another question from Dr. Saravana Kumar. How the regions are bind together without any defects?
How the regions?
Maybe he's talking about the
layers.
Yeah.
Okay. If I understand the question correctly, so we actually go, like, we prepare the device in a layer by layer fashion. So we take F2O and then we coat titanium, and then we coat perovskite on top of it through solution process, all through solution process. So since you go with solution process, like there is, you just coat over and over. It's like assembling layer and layer. That's all. It's like preparing a cake. You take a base and put a cream, and then put a cake again. Yeah, it goes on something like that. So there is no need for, how to say, specific interaction or binder or something. Since it's a solution process, everything just sticks together. Or even you can evaporate on them. There is this, the physical interaction between them is enough to hold these layers together.
Okay. So Dr. Manoharan is waiting in our Zoom room for a long time. And there is no more questions, but people are appreciating you.
Thank you.
Please,
Thank you all for
please,
the
please
attention.
go through it, and please stay along for some more time if you have free time. Next, we will move on to session 4. Now I invite Dr. Jayakumar to introduce our speaker, Dr. Manoharan Mariappan.
I closed this window anyway.
Yeah.
So thank you so much.
Yeah. Next speaker, Dr. Manoharan Mariappan from North Florida College, USA.
Shall I continue, ma'am? Can you all hear me?
Just a minute, we will connect with Dr. Manoharan, sir, with audio and video.
Yeah, I can hear.
Good afternoon, sir. I mean, good evening, good morning, sir.
Good morning for us. It's fine. Thank you.
Thank you, sir. You're very welcome, and you're sorry to keeping you wait for long.
Oh, no, it's fine. For me,
Okay.
okay.
So
Thank
we
you.
shall, you're very welcome, sir. We shall move to session 4 straight away. Now I invite Dr. Jayakumar to introduce Dr. Manoharan Mariappan.
Thank you, ma'am. I hope you all can hear me.
Yes.
Respected delegates, dignitaries, fellow teachers, research scholars, and student friends. A wonderful good morning, good afternoon, good evening to you all present in this globe. I take immense pleasure to introduce our research personality, Dr. Manoharan Mariappan, sir, who have a very fantastic research career ever since he's completed his PhD, probably around 1997. He completed his PhD at Bharidasan University, India. His PhD thesis centered on Diels-Alder cycloaddition reactions involving Quemelin, heteroquemelin, and quantum computational studies. Then, within 2 years of time, he kickstarted his career. He started as a postdoc at Free University Brussels, Belgium, and he worked there till 2000. Around 2001, he shifted to University of Arizona, Athens. And again in 2006, he took a great leap in his career by gaining a research associate position at Florida State University. Then, probably sooner or later, he became, or he elevated his position to assistant professor level. Then soon following, he became associate professor at Bethune-Cookman University. He stayed there till 2017, and now presently he emerged as a professor of chemistry. So he has a very great elevation ever since he's completed his PhD. That is around 1997. So now he's working as a professor of chemistry in North Florida College, Florida, USA. To his credit, he also given a position of adjunct chemistry faculty at Tallahassee Community College, Florida. The research interest of Sir being mainly involves computational and theoretical chemistry. The study scatters between aromaticity, stereoelectronic and stereoelectronic effects, and hydrogen bonding effects. His research pursuits focuses mainly on novel radical cyclization of alkenes, alkynes, and aromatic system. In addition to that, polyaromatic simple graphene systems happens to be his main target of research area. Also, he published numerous research papers in a various reputed journal to and thank you very much for the participation. Thank you, sir. Session is over to you, sir.
Thank you. Thanks for your introduction. Thank you very much. All right. So good evening, guys. I think this is your tea time. So I hope you're awake after having your tea. All right. So yeah, he already introduced about me. Right now, I'm at North Florida College, where I'm teaching chemistry most of the time. My research has been reduced to the extent, I would say that. And I'm not doing that much research, but I'm doing a little bit of research in collaboration with other professors. So because of my family, I moved back to my hometown. That's the capital of Florida. So that's the reason why I'm teaching mostly chemistry courses in the local college. Okay, so that's the reason. All right, so today I'm going to talk about the stereoelectronic effects on organic structure and reactivity. So the title is a little fancy, but you already learned something about stereoelectronic effects in a master's level, not in undergraduate level, maybe a little bit in undergraduate level. So not much in undergraduate level, mostly in master's level. Okay. So to learn stereoelectronic effects, so like Culvertical, okay, so Rosetta Stone. So the best way to learn the stereoelectronic effects, to follow these two different books, Stereoelectronics by Kirby, and the Stereoelectronic Effects written by Igor Alabugin. He's a Russian chemist. So I was working with him. So in this book, half of the materials are from my own research, I would say that. Then natural bond orbital, NBO, that's called NBO. So it's written by Frank Weinhold. So he's one of our collaborators. So most of the stereoelectronic effects depend on this theory, NBO theory. All right. So it's very, very simple theory, which is implemented in Gaussian program and other quantum mechanical programs. Okay. Okay, before we get into stereoelectronic effects, let's categorize the electronic effects. So what are the main electronic effects you learned in master's level, or you're learning in the current master's courses? Okay, especially in organic chemistry. So what are those electronic effects? Inductive effect, yes. So you realize the inductive effect by electron transmission through the sigma bond. That's very important, through the sigma bonds. Okay, so that's the most important thing. All right, so this can be plus I effect, minus I effect, depends on the group. So this is ammonia, it's ammonium group. Okay, so amine group, basically this is nitro groups. So amine is electron rich.
Excuse me, sir.
Yes.
Would you like to share your screen? We are not able to see your screen.
Oh, I'm sorry.
Oh, that's all right. That's all right.
Okay. Oh, something had happened. Yeah. Oh, host disabled participant screen. I don't know why. Oh, I thought it's.
I will ask my technical team to
Yeah,
help you, sir.
I thought it's enabled. Yeah, it looks like it's been disabled.
All right. Sorry about that.
It's okay. It's okay. Yeah, it says host disabled participant screen sharing. I don't know why.
Yeah, I will call them, sir. Just a minute.
Yeah, not a problem. I don't know what the problem is. I thought I shared it. I clicked it. Or can I close it and come back?
Sir, can you please wait for a minute? He's going there to the system,
Oh, okay.
and
That's
he's
all right.
he's looking at it, sir.
It's okay. No problem. It happens sometimes. Conducting webinar is always challenging.
Yes.
Maybe technical issues.
Yes, we are new to this thing. We used to have people around us to help when we have seminars conducted in the halls. But now we are not able to get any assistance, and we are just learning everything and conducting
Okay.
webinars.
No problem.
We are completely depending on a technical team. They are simultaneously doing two works. They are taking care of the admission and the conductance of this webinar. So that's a delay in it.
That's okay. Maybe I will leave it and come back. Is that okay? Can I try that way?
Yeah.
I will leave the meeting and come back. Yeah,
yes,
let's
sir.
try that.
Yes,
Let's try that.
Yes, sir.
Ma'am?
Yes, sir. Understand, sir?
What's the name, ma'am?
Dr. Manoharan.
He's not in list, ma'am.
He'll be back soon. He had just left, and he'll be back soon. He's in the list. Manoharan Mariappan. Sir, Manoharan, sir?
Yes.
Yeah, technical team is there to assist you. Dr. Veniston, sir?
Now you can, now sir can share the screen.
Okay. Sir, please share your screen.
Oh, now I can share it. Yes, that's possible. Sorry.
Okay. Sir, one more.
Oh.
You have an option in more, the top of the screen.
Okay.
Manohar, sir?
Yes.
Yes, sir. You have an option in the top of the screen in more option is there.
Yeah.
Then click and disable participants annotation.
The more option. Yes, I saw somewhere right now. I don't know. Yeah, here it is. Disable participants annotation. Okay.
Okay, sir. Go ahead. Thank you.
Is it okay? Okay.
Yes, sir. Thank you.
I did it.
Okay, sir. We should start,
Yep.
sir.
Thank you so much.
Very welcome, sir.
It happens sometimes. All right, so maybe I'll start again. So the topic I'm going to talk about is stereoelectronic effects on organic structure and reactivity, right? So this may be a new topic for you guys as far as the title is concerned, but you already learned it in master's level. So these two are the major books we follow. You can also refer these books. Stereoelectronic Effects by Kirby, and then by Alabugan. So Alabugan he was my postdoc boss at FSU, Florida State University. So in this book, you will see half of my research works. All right. So to learn the stereoelectronic effects, so we need to depend on natural bond orbitals theories. So it's written by Frank Weinhold. He's at University of Wisconsin. He's one of our collaborators. So these are all like Rosetta Stone of stereoelectronic effects, like culvertical. So that's what we say. So this is the best way to learn. Okay. So very, very fundamental aspects of organic chemistry. So which required for organic reactivity study and other reactions. Okay. All right. So let's worry about the electronic effects. So let's categorize all the electronic effects that you learn in organic chemistry. So inductive effect. So what does inductive effect means? So there is an electron transfer through the sigma bond. So it can be plus I effect or minus I effect. Okay. So this is amine group, electron rich group. There is an electron donation through the sigma bond. Here, this is nitro group. Nitro group is electron poor group. So it attracts electron from the ring. So that's what it happens. Okay. So this is a simple inductive effect. Then another major electronic effect is resonance. So the resonance effect, how to draw the resonance structures for simple and bigger systems. Okay. Neutral or ionic systems. So this is ozone. So you see the resonance structure of ozone. So this is delocalized structure. Okay. So this is the hybrid of these two structure. Hybrid. So this is the hybrid form of these two resonance structures. This is called delocalized structure. Okay. So pi electrons are delocalized. So when you look at the molecular orbital, you will see the structure that looks like this. All right. So that's the basic stuff which you already learned. All right. So another important effect, mesomeric effect. Okay. So mesomeric effect in which you can realize the polarity of the bonds, polarity of the molecule. Okay. So through resonance only. This is part of the resonance structure. Then the last part is hyperconjugation and anomeric effects. So these two are important. So these two are important in chemistry. So they are part of stereoelectronic effects. So these two effects you already learned in organic chemistry, very basic organic chemistry. All right. So sigma delocalization. So through bond resonance. So you might have heard about hyperconjugation in different forms. All right. So anomeric effect. So anomeric effect always happens between the oxygen lone pair or sulfur lone pair that interacts with a sigma star. Okay. So anyway, we will explain this in the later section. All right. So this is hyperconjugation. Hyperconjugation is an interaction between sigma CH bond or sigma CC bond and sigma star, donor and acceptor. So this is donor. So this is donor. So this is acceptor. Okay. So sigma star. So there is an interaction between donor and acceptor. Likewise, you can see that. So the lone pair is a donor. This is an acceptor. So, all right. So how this is going to work? So what are the conditions? So that's what you need to worry about before we learn a complete picture of electronic effects, stereoelectronic effect. All right. Oops. Yeah, that's okay. So let's worry about the structure and reactivity, going beyond the undergraduate chemistry. So let's take a small quiz. So here you see a series of molecules, okay, in which you see two different conformations or isomers, whatever it is. All right. So in these cases, you see fluorine as a group, fluorine system. So fluorine changes the stereoelectronic effect and other electronic effects in different way. So we think that this is anti. Just a second. Yeah. So look at that. So usually anti form is more stable than gauche form, but in this case it's not like that. Okay. So it's going to be working opposite. So why this is happening? So this is all because of donor acceptor ability of the groups. All right, so here cis is more stable. Usually trans is more stable. Okay, so in cyclohexane conformation, equatorial position makes the cyclohexane to be more stable than axial. But in this case, axial is more stable because of anomeric effect. Okay, same situation happens in the dioxane, 1,3 dioxane. So look at this. Both are axial. So axial is more stable than equatorial. Why? Because of donor acceptor ability of so this is donor. Okay, so CH. So this is sigma. So acceptor. So sigma star. So the interaction between axial bond is stronger than equatorial. So this is equatorial and the equatorial bond. So that's what it happens. Okay, sorry. So this one, right? So that's so this is totally opposite to what we expect. Okay, so but in the simple system, we realize the same effect. Okay, so anti is more stable. So is there a common theme? Yes, we can make a common theme by using a simple system. Okay, without any substituents. So in this case, anti is more stable. That's what we learned. Ethane, in which anti conformation is more stable than syn conformation. Okay, syn. Anti is more stable. So S trans is more stable than S cis. Here, the two hydrogens are trans to this double bond. Okay, so that's why it is more stable. So look at that. So let's part it. Which one is more stable? So anti is more stable. So S trans is more stable. So this anti conformation is more stable than the syn conformation in the allyl system. This is allyl system. When you look at the ester system, so this is more stable than the other one because this lone pair. Just a second. Yeah, I'm trying to use the pen. So this lone pair is anti to this bond. Okay, so there is an interaction between lone pair and the sigma system, not the pi system. Okay, so that's very important. Okay, so through bond interaction, but this is syn to each other. So there is an overlap between these two. All right, so here also same situation happens. Okay, so this is what we study. So these are all the electronic effects so which can be realized through the stereoelectronic effect. So what is stereoelectronic effect? The impact on the structure, reactivity, or physical properties is caused by the spatial arrangement. Underline that word. That's the most important thing. Spatial arrangement of the orbitals. So 3D arrangement, okay, of the orbitals in the molecules electronic structure. So that's the key thing. Okay, so in any structure you can realize the stereoelectronic effects. And so stereoelectronic effect plays a major role in the structure, stability and reactivity. Okay, so let's go one by one. So before we realize the stereoelectronic effects, let's worry about the main stereoelectronic rule. So what is the main stereoelectronic rule we need to follow? Even though it doesn't work for some cases. For example, I just talked about fluorine case. So difluorine substituted case, it works opposite. Okay, so that is exceptional. So that's totally different. But still, stereoelectronic effect plays a major role. I will explain it later. So the main stereoelectronic rule. So which one takes care of the stereoelectronic effects? Anti-periplanar position of sigma and sigma star. Okay, so sigma and sigma star. So anti-periplanar. So sigma and sigma star. So one will be sigma, another one will be sigma star. So in this case, this is sigma, so this is sigma star. So some people use the word coplanar, anti-coplanar. So it's fine. Anti-periplanar or coplanar, they're all the same. So this is gauge form. So you might have studied in even in undergraduate. So this is staggered form, eclipse form, staggered form. So in which, if these two groups are opposite, that's called anti-form. Two bulky groups are, they're adjacent in the staggered form, that's called gauche form. So probably you know that. All right. So in this case, okay, anti-periplanar position is the most important to realize the stereoelectronic effects. Okay. All right. Yeah, this is a nice picture, which is provided by the NBO, developers. So this is a nice picture. This is the anti-periplanar orientation of, sorry, I'm trying to use the annotation one. Yeah, that's the one. So this is sent periplanar in orbital overlap. So 3D interaction between two different orbitals, sigma and sigma star. Okay. All right, let's move on to other one. All right, so anti-periplanarity. So that's the main stereoelectronic rule. So it also depends on the energy. So how you're going to prove that this is dominated. So this is overwhelmed. I mean, stereoelectronic effect is overwhelmed by using the energy factors. Okay, so the energy plays a major role. So between syn and anti, look at that, anti is more stable than syn by 2.7 kilocalories. So likewise, you can see in all cases. So in this case, anti is more stable than syn. So you can see everywhere. So we feel that, the anti-periplanar orientation of, sigma and sigma star is responsible for this stability. But there may be some other factors. So however, the differences in conformer energies can potentially originate from multiple resources. We don't know, something may be hiding, but still the combination of various stereoelectronic effects may give a solution to explain why this is stable. Okay, so that is possible. Okay, so you can think about other factors in the controversy. So I will leave it to you guys. Okay. All right. So how we are going to realize the stabilizing orbital overlap by anti-periplanarity? So just by using the natural bond orbital energy. So this is the equation which is heavily used to we used to know the energy of interaction between sigma and sigma star. Okay, so that's the main thing. So just a second. Yeah, just 1 second. I'm trying to use that one. Oops. Come on. Yeah. So this is the new software. This is from the old software. So when I was doing my postdoc, I was using this software, but nowadays, this fancy software is available to show the stereoelectronic interaction. I just wanted to tell you. So it's all right. Okay. So types of hyperconjugation. So types of hyperconjugation. There are 3 different types. So when you handle the neutral molecules, it's called neutral hyperconjugation. If you handle the anionic systems, okay, so if it's anion, it is negative hyperconjugation. If it is positive charge, if there is a positive charge, okay, if the system is cation, that's called positive hyperconjugation. That's all. They just categorize it. Okay, so you can have your own name. If you have radical, you can say radical hyperconjugation, something like that. Okay. So this is another definition. I'm just showing it to you guys. So stereoelectronic effects is an interaction of electronic orbitals in the 3D space. That's all. Very simple definition. Okay. So you got to be very careful when you use the the word stereoelectronic here. So it's not a combination of steric and electronic. It's stereoelectronic effect depends on the stabilizing interaction between two different orbitals, sigma and sigma star. That's all. Okay. So it happens through the 3D environment. Okay. All right. Okay, so why do we have to worry about stereoelectronic effects in organic chemistry? So stereoelectronic effects, interactions can be quantified by using some computations. That's the main thing. Okay? So it can be easily quantified by the natural bond orbital theory. All right. So that will allow us to know the stability of the structure, the relative reactivity, stereo and regioselectivity of any organic reactions. Okay, so it's very useful for the development of organic synthesis in recent days. Okay, also it's been entered into biochemistry and pharmaceutical chemistry as well. So how we are going to quantify the stereoelectronic factors in organic structures, mainly in organic structures. Okay, so mainly in organic structure. So by conformational changes, isodesmic equations or homodesmotic equations, and then localized wave functions. So that comes straight from NBO dissection, okay, in the form of energy. All right. So let's worry about the conformational changes. So this is a simple anomeric effect which exists in the Perovskite system. Yes, Perovskite system. So look at this. Axial substitute, axial methoxypyrene. Okay. And then just a second. So this is axial, sorry, this is equatorial methoxypyrene. So this is axial methoxy. So which one is more stable? Which one is more stable? So because of this lone pair, okay, so this lone pair is anti-periplanar to this CO bond. So the interaction between oxygen lone pair and sigma star, CO is stronger than this one. Okay, so this lone pair and the CH bond. Why? Naturally, because because electronegative oxygen, because of electronegative oxygen. Okay, so that's possible. So that's why you see that. So the arrow forward reaction is faster than reverse reaction because this is more stable. So this is more stable by 3.6 kilocalories. So it is negative because product is more stable than reactant. That's why you see the negative value. Okay. All right. So that way you can realize it. So this is a very, very simple system to realize how anomeric effect works. All right. Also, you can see the specific interaction energy. So that's what you see. So, okay. So that's the specific interaction energy, but I haven't shown it here. But in the later slides, you will see something. Okay. All right. Okay. By homodesmotic equation, isodesmic equation, you can prove that. Okay. So which one is more stable? So in this case, it is equally stable, 1,4-dioxane and 1,3-dioxane. Even though you show the stereoelectronic interactions between oxygens and CC bond, CO bond. Okay. The final one is natural bond orbitals. So the natural bond orbitals are derived from natural hybrid orbitals. Natural hybrid orbitals are derived from natural atomic orbitals. The natural atomic orbitals are originally coming from Schrödinger wave equations orbital psi. Okay, so that's how Frank Weinhold has defined. Okay? So finally, he came up with this energy. So the interaction energy. So that's the interaction energy between sigma and sigma star. So in pyrene system, so look at the interaction energy, 14.1 kilocalories per mole. That's huge. So you can say that because of this interaction energy, the axial group is more stable than the equatorial group. So it's very useful. This NBO analysis is really useful to analyze the stereoelectronic effect. All right. Okay, so we think that we care about one particular interaction, but there may be some other interaction. It's a multiple interactions. Okay, so multiple layers of, you know, just a second. Oops. Yeah, multiple layers of, you know, delocalizations occur in some cases. Okay, so for example, so look at this, you know, carbonyl system. So this is aldehyde, so this is ketone. So in this case, so the conformer you see the left hand side is always more stable than the right hand side. So why this is happening? So that's because of the stereoelectronic effects. All right, so we simply say that it's because of stereoelectronic effects. So in this case, in the ketone system, so the right hand side, so look at that. So in this case, it is doubly eclipsed. Okay, so doubly eclipsed. So the interaction between two sets of CHS, okay, so they are overlapping with the sigma star of this one. All right, so double effect. So that's what we think that, but you know, there may be so many interactions. Okay, not just that. Okay, so there are so many stereoelectronic effects. So can we simply use the short explanation? So the preference of two CH bonds to the anti and coplanar of the CO double bond, okay, pi star system. So this explanation is not enough. So, oops, sorry. So when we analyzed each and every interaction, so we came up with some energies. Okay, so for each and every interaction, okay, so this is first set of interaction, second set of interaction, third set of interaction. All together, we observed some energy. This is the net energy of all those interactions. All right. So finally, we prove that, so the combination of all these interactions are responsible for the stability of, okay, so stability of, you know, these groups. Okay, so these groups, so this is anti-periplanar, but this is not, this is syn periplanar. So qualitatively we can say that this is more stable than this. Why? Because these CH groups are anti to CO bonds, but not this one. This is syn to this one. But quantitatively you can say that the combination of these interactions are greater when compared to the other one. You see that? So that's how you know, these kind of researches are successful, okay, by using simple computations. Okay, so we prove that, we quantify the factors, you know, behind this qualitative idea. So this is just a qualitative idea. So this is quantitative treatment to that qualitative, you know, thinking. Okay, all right. All right, so next aspect is, okay, so this was the first work, you know, we started with this simple hyperconjugative, you know, acceptor ability of CX bond. Okay, so you will be surprised. We used simple ethane system. Think about it, just ethane. This is just an ethane system. Ethane system in which one of the hydrogen is replaced by some groups. Methyl group, you see that, silane group, you know, germanium, you know, derivative, and then the nitrogen groups. Okay, so nitrogen family. Okay, so group 5 family, nitrogen groups, phosphorus groups, you know, arsenic group, and then group 6 family, 7 family. Okay, so halogens. All right. So what is the purpose of doing this? So we try to realize the hyperconjugative acceptor ability of CX bond. Okay, so acceptor ability. So where is the donor? So this anti-periplanar orientation of this CH is the donor. So that is trying to interact with the CX bond. Okay, CX bond. So let's see how this trend looks like. So what we observe based on this. First, we try to correlate electronegativity and the polarization of CX bonds. So you know that this is polar. This is polar bond. Definitely this is polar. Why? Because you have carbon and X bond. So X can be, so all these groups. Okay. But carbon-carbon bond is not polar. You guys know that. So that is not that much polar. Okay. It is non-polar. But still, to understand the trend in that group, we just added, carbon. All right. So what is the trend? So the trend is clear. The correlation between electronegativity and sigma star, okay, sigma star CX bond, the polarity, it is clear. So then we moved forward. To analyze other things. So now we looked at the sigma star energy. Okay, so sigma star energy. So what's going on? So now we correlated. Afterwards, we correlated electronegativity and sigma star CX bond, because that's the main thing. Okay, so lower the energy, greater the interaction. So look at that. All the halogens are showing lower energy. So halogens are a better acceptor when compared to other groups. That's what we proved first. So that's why halogens are used as a leaving group in SN2 reactions. So that's the proof. Okay. So look at that. The strongest acceptor ability of carbon halogen bond actually gives an evidence for why halogens are a good leaving group in SN2 and E2 reaction you study in undergraduate and organic chemistry. So this is a nice proof. Also, look at the energy contribution towards this interaction, towards CH and CX interaction. So you see a nice trend by period, each period, like you see here by period. Okay, so because CX bond has lower energy, so that can interact strongly. Here we realize the interaction energy is stronger towards halogens. Okay, CX bonds are a better acceptor. Okay, so we prove that. So this correlation is just for our record, how the electronegativity is correlated with the CX bond when CX acts as a donor. So look at that, just a donor, it's not sigma star. Yeah, that also shows somewhat good correlation. Okay, but that's not important for this study. Okay? All right, so we moved on to some other system. So this is ether, ethyl methyl ether. So in ethyl methyl ether, so here we realize directionality. So how you see the direction of stereoelectronic effects. Okay, so here we observe two different interactions. The first one is CH and CO interaction. So this is sigma. So this is sigma star. Okay, and another one is opposite to that, CH and OC interaction. Look at that, OC, not CO. That's what you see here. OC, this is CO. So which one is greater? So we found that CH and CO interaction is greater than CH and OC interaction. So the difference is 1.2 kilocalories. So look at the nice picture of stereoelectronic interaction. So multiple effects. Okay, but still the combination of those two interactions are important. Okay, so this is a nice stereoelectronic orbital, so molecular orbital overlap picture. Okay, all right. Just a second. I don't know where they are. I tried to delete this stuff. Yeah, that's the problem with the Zoom sometimes. Yeah. I don't know where they are. Okay, I'll try. Okay, so now I don't know how to delete. I don't see those icons, delete icons. All right, I'll try to manage that. Anybody has any clue?
Just a minute, sir. I think you can hear me. Go for this annotation. And the annotation, you will be seeing the eraser rubber, and you make you, or otherwise you can go for clear all screen.
Oh, right. Now I can see it. Sorry. Thank you so much. Yeah. In the annotation, that's the reason. Yeah.
Thank you.
I barely use Zoom. we use different platform. Yeah. Big blue button, something like that. Yeah. All right. Okay, so I got it. Thanks. Okay, so now let's worry about the Anomeric effect. You know the history of Anomeric effect. Mostly, in the beginning, they use glucose systems. Okay? So carbohydrate systems. So it was first observed in 1955, and then 1958, the Anomeric effect was suggested by Lemieux. So this is alpha D-glucose, beta D-glucose. So they are relatively stable. Okay. So look at the system you see here. So beta D-glucose is more stable than alpha D-glucose. Okay. So look at the percent yield. So this is greater. Okay. So in this case, when compared to this, so this is more stable. Because of the lone pair and the CH bond. Okay, so the CH bond, so that's sigma star. But if you look, when you change the OH group by O-methoxy group, it's totally different. So the lone pair, oxygen lone pair and CO interaction is greater than the CH interaction. So it gives a reversal trend. So 67%. Okay, so axial orientation. That's purely because of anomeric effect. So likewise, you can see that acyl group and chlorine, definitely Cl bond is a stronger acceptor. We just saw that in the simple ethane case. Okay, halogen bond will make the CCl bond to be a greater acceptor. So that's what it happens. Okay, so that's why you see 94%. Okay, so axial oriented, this glucose. So you guys know that the Splenda recently, the sweetener Splenda, this is a modified form of glucose, Splenda. So Splenda has chlorine system. So chlorinated, sucrose, chlorinated sucrose. It's just for your information. All right. So anomeric effect also can be, explained based on the polar effect, Coulombic interaction, and then hydrogen bonding patterns. But still, you can mainly discuss the hyperconjugation. So that's the one. Okay, so that's the hyperconjugation. Okay. Yeah, so this is the same thing, but it's different, a little bit different. So there are variety of anomeric effects. The first one is called endo-anomeric effect, exo-anomeric effect. So what is the difference? Endo and exo-anomeric effect. So endo-anomeric effect means, okay, so here is a lone pair. So the lone pair is in okay, pair interaction CX bond, within the cycles. Okay, so that is endo. So in this case, okay, so the lone pair is coming from outside and interacting with the sigma bond. So that's what it happens. Okay, so this is exo-anomeric effect. So that's the difference. So the lone pair is inside the cycle here. This lone pair is outside the cycle. So that's why they name it as exo-anomeric effect. All right. Okay, in esters, so we already saw some examples. from carbonyl groups, but this is ester. So ester, in which you have an oxygen lone pair. The anomeric effect can be realized from this oxygen and this sigma star or pi star, both. Okay. So this is more stable than this. Why? Because this lone pair is syn to this C double bond O. Okay? So this is syn. So, but this is anti. So everywhere you see anti. So anti-periplanar. So look at that. So that is anomeric. Anti-periplanar. They're opposite, right? So the energy difference is 4.8. So 4.8. So in this case. So when you have methyl, it is a little bit higher. Why? Because it is electron rich. So it increases the energy difference. Okay. All right. So the next aspect is towards peroxide. So this is another interesting observation. So we made. Okay. So does peroxide show stereoelectronic effect? So the stereoelectronic effect in peroxide is very weak. That's what we proved it. So that's what we proved it. So CO bond is rotable. CO bond is rotable. At the same time, we all know that peroxide bond is very weak. It's very weak. It can be easily broken. That's why peroxide is used as an oxidizing agent. All right. So that's a different story. That's about reactivity. But look at the structural aspect. The structural aspect. The energy difference is very little. Okay. So this is free energy. It's very minimum. But when you look at the stereoelectronic interaction, so look at the energy. This energy is very, very tiny. That's nothing. That's negligible. So that's why we confirm that stereoelectronic effect is not important in the case of peroxide. So the anomeric interactions are not important finally, because it is related to oxygen lone pair and the CH, some sigma bond, sigma star. Okay. All right. But we immediately compare the similar system. Okay. Similar system. So this is ether. We already saw that. So here you see the electronic interaction, stereoelectronic interactions. So it's huge. Okay. It is similar system. Because of peroxide, we lose the stereoelectronic effect. Okay. All right. So another interesting thing. So we compare the peroxide with the acetal system. Another isomer. Okay. The molecular formula is same, but the structure wise it's different. So why do we have to worry about peroxide? Because peroxides are heavily used in medicines, also in explosives. Okay. So these are all the compounds which are used in medicine and explosives. I mean, used as some explosive materials. Okay, so this benzoyl peroxide is used as a radical initiator. All right, so this is another one. It's just for your information. All right, let's worry about the conformation, the real conformation. So look at that. So here we compare the peroxide with the acetal system. Okay, so acetal system. All right. So here we have two oxygen bonds. They are adjacent. Okay, they are adjacent, but here two oxygens are arranged in alternate fashion. Okay, so we are going to prove that there is no stereoelectronic effect here. This rotation is due to stereoelectronic effect. That's what we have proven. So look at that. Oops. Yep. So here double rotation is possible. Here only one rotation. So that's because of the stereoelectronic effects. Okay. Oh yeah, this was provided by our grad student, this guy. He's a Brazilian guy. So here you see the energy profile diagram for both systems. So this is acetal. So this is for acetal. Just a second. Yeah, this is for acetal. This is for peroxide. Just one barrier. Okay, so one barrier by single rotation. Okay. So when we analyze the orbital interactions and their energies, you see that the energies are very, 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 very minimum. So look at that, the total energies. So only this much. But here it is 14.9. So that's huge. So it is fully stabilized. It is strongly stabilized by the stereoelectronic interaction, but it's not. It is weakly stabilized, peroxide. So peroxides do not depend on the stereoelectronic effects. Okay. So that's what we proved it. All right. So another effect is called, alpha effect. So what is alpha effect? So alpha effect, intramolecular. Intra means, within the molecule. Intramolecular alpha effect. So there is inter too. That's a different story. So this is intramolecular, alpha effect. So what does that mean? It's almost the same as anomeric effect, but that particular lone pair is adjacent to. Okay, so it's basically a. I'm sorry. So this is adjacent to another pi bond. Okay, so it can be pi bond or another lone pair. Okay, so pi overlap. Okay, so there is a donation towards CF sigma star. Okay, so when we analyzed the alpha effect. Okay, so when we analyze the alpha effect and anomeric effect, which one is greater? That's what we try to analyze. So look at the anomeric effect. So the energy of anomeric effect due to stereoelectronic effect is greater than the energy of stereoelectronic effects due to sigma effects. So sigma effect is due to peroxide. Okay, anomeric effect is due to just one oxygen. Okay, so this is still greater. Anomeric effect is still greater. Alpha effect is a little bit less stable due to stereoelectronic effects. So this is another application towards peroxide. So this is another proof why peroxide is less preferred as far as stereoelectronic effect is concerned. Also, you can talk about some other aspect, because oxygens, they are close each other. So there is a lone pair repulsion that may lead to, destabilization. So that's possible too. So that's a qualitative, explanation. Okay, so the next aspect is, the stereoelectronic effect in supermolecular systems, especially hydrogen bond. So hydrogen bond, in which you always see the interaction between the hydrogen acceptor, the lone pair of oxygen and here water. Okay, so that will interact with CH bond. So this is CH bond of another water molecule. So this is lone pair. So N2 sigma star, OH sigma star. So that is the major stereoelectronic effect. So when we collected the NBO data, so you see that lone pair to sigma star is roughly 9.5. That's huge. 9.15 kilocalories per mole is really huge. In kilojoules, that's even greater. Yes, times 4.184. So that's huge number. Okay. So hydrogen bond actually stabilize the water dimer. Okay. So that's how water is stable in the liquid form. Okay. Then think about the ice. That's even more stable because you will see a lot of hydrogen bonds, more hydrogen bonds in ice. All right. So again, when we look at the directionality of the hydrogen bonding, so I already showed that. So this is a nice picture which shows N2 sigma star, N2 sigma. Sorry, and come on, N2 sigma star. So here we have some other examples. The lone pair of nitrogen that interacts with the XH bond. Same thing here. So here oxygen and XH bond. Okay, so the angle is different here. So here, look at the angle, which is different. So the molecular axis, but still the hydrogen bond is showing the stereoelectronic interactions. That's the major thing. Okay. All right. So here, we are comparing carbonyl system and sulfur system. Okay. So look at the molecular axis, which is different. Why this is happening? So molecular axis in the carbonyl system is different from C double bond S system, the derivative of carbonyl system. Okay. So why this is happening? So because of the lone pair of sulfur and lone pair of oxygen. So here the sulfur lone pair is more diffused. The orientation of the sulfur lone pair is different from oxygen lone pair. Naturally, it is occurring. Okay, so that's why. So accordingly, the hydrogen bonding pattern will change. So that's why they have asked the question: why are thiocarbonyls are different? Because of the lone pair orientation. Okay. All right. So this is our main part of our research. So we we invented something, by comparing the regular hydrogen bond with the improper hydrogen bond. So a proper hydrogen bond with the improper hydrogen bond. So proper hydrogen bond is called red-shifted hydrogen bond. The proper hydrogen bond, regular hydrogen bond, I would say regular, normal hydrogen bond, red-shifted. The improper hydrogen bond is called blue shifted. So what is the difference? So whenever you realize the hydrogen bond, so the hydrogen donor, okay, the CH bond will be elongated. It will be stretched. Okay, it will be stretched. So you can realize the IR frequency. Longer the bond, lower the frequency. So you guys know that. Okay, so longer the bond, lower the frequency. So you will see a lower IR frequency. If you look at the improper hydrogen bond, the XH bond will be contracted. Okay, so it will be shortened. It will be shorter than the monomer structure. Okay, so monomer bond, monomers, CH bond or other SH bond. So if you look at the IR frequency, so the IR frequency will be greater when compared to the monomer. So we are comparing, for example, methane systems. We can take simple methane. That's easy. So CH bond. So assume that this CH bond is like 1.12 angstrom. Okay. So after it interacts with some other group, okay, some donor, okay, okay, so with the lone pair. So this CH bond will be elongated. So it will become 1.2, 22, something like that. Sorry, 1.1525, something like that. So it will be elongated. So that is called redshifted hydrogen bond. So that is the proper hydrogen bond, normal hydrogen bond. Okay. So improper means that CH bond will be shortened. It will become stronger. So automatically, stronger the bond, higher the IR frequency. Okay, so higher the IR frequency. So this is like this is just for fun. So proper, improper. So in the US, the red regions are, Republican, blue regions are, Democrat. So now there is a competition between red and blue, between President Trump and Joe Biden. He used to be the vice president before, when Obama was the president. So now that's what it's going on. So there is a controversy between improper and proper hydrogen bond that's going on these days. Okay. So this is the stereoelectronic effect. You realize the hydrogen bonding towards hydrogen bonding system. Okay. So this is the orbital picture. Okay, so in our case, we use CH, CH CH, F3 system. What is the purpose of doing this? So this 3 fluorine group, okay, these 3 fluorine groups will allow the CH bond to be the improper hydrogen bonding group. So that's what it is. That's the idea. So you can have chlorine too, chlorine too, so not bromine, because bromine is less electronegative when compared to chlorine and fluorine. So that's what we handle. So by using CHF3 group, okay, by changing different hydrogen acceptors, we handle this problem. So look at that. The HY distance against, CHY distance. So this is, proper hydrogen bond. This is improper hydrogen bond. Okay, so improper hydrogen bond. So there is a small variation. So that's what we observe. So that's because of contraction of CH bond in improper hydrogen bond. So that's what we realize. So it's been proven by this CH bond parameters first. Okay, and then we move forward. So this paper was published in, Journal of American Chemical Society. Okay. So then we compare the same, HY distance with the, S character. So what is S character? How do you get S character? So when you have this one, so what is the hybridization of this carbon? The hybridization of this carbon is, sp3. Everyone knows that. Okay. So what is the S character? In here? So the S character. So theoretically speaking, the S character is roughly this is 1/4. Okay, 25%. But it changes. Look at that. So S character is, between 32 to, 36 because of this fluorines. It changes. Okay, so that quantity is different. But look at the difference between, red shifted and blue shifted. Okay, so it is clear. Okay, same thing happens. The polarity of the CH bond. Okay, so everywhere the improper hydrogen bonds, property is, the quantity based on each property is lower than the red shifted hydrogen bond. So that's what we proved it. Okay, so because of CH bond contraction. Okay, so that is clear. All right. Okay, the next aspect is, Homo Anomeric effect. What is Homo Anomeric effect? Anomeric effect. Anomeric effect is nothing but the lone pair of one of the heteroatom and the adjacent bond. But this is not adjacent bond. It is alternate bond. So this lone pair, okay, so the lone pair of some heteroatom interacts with the alternate, CH bond or some CY bond. Okay, so that's what it happens. Even though it's very, very minute, but there is stabilization due to that lone pair and the alternate bond. So whenever you pick up the equatorial lone pair, that's called W effect. If you pick up the axial lone pair, that's called Plough effect. Okay, so that's a common one. So this project has been, designed based on the simple, SN2 reaction. Okay, SN2 reaction. All right. So look at that, the interaction between nitrogen lone pair and then, this sigma star. Okay. So we have chosen these kind of systems for our studies. This paper was published in, JACS again, but very simple work. It's like an undergraduate work, but this has been published in, JACS paper because the study is new. All right. Here, based on our study, all right, here you see that the equatorial lone pair interaction with the CH bond, axial lone pair with the CH bond. Okay, so which one is greater? That's what you need to worry about first. Okay, so here axial lone pair is greater than equatorial. So look at the interaction. You see that there is an interaction. Here, the interaction is very little. Okay. All right. Same situation, but here it's different, little bit different. So this is equatorial bond, but this is axial bond. This contribution is, little bit less when compared to this. Okay. Compared to this. So in this case, equatorial lone pair is interacting with the CH bond little greater than the axial. All right. But overall, in tetrahydropyron, tetrahydrothiopyron, selenane, so pi lone pair means axial lone pair is better donor than sigma lone pair. That's what we proved it. Okay, so in piperidine is different. So this is all piperidine system. In this case, it worked opposite. Why this is happening? Because piperidine, in which nitrogen has only one lone pair. So the arrangement of the lone pair made it different manner when compared to oxygen. Oxygen has two lone pairs. One is equatorial lone pair, another one is pi lone pair, sigma and pi. Okay, axial and equatorial lone pair. So here the interaction, based on these interactions, equatorial lone pair interacting with the CH bond, equatorial CH bond is greater when compared to axial. It shows the reversal trend. So that's what we proved it. So this is all new observations. Okay, so this is all new observation. No one studied before. Okay. All right. Yep. So this is a nice graph, which shows categorically. So the energy contribution towards Homo Anomeric effect. Okay. So here we see a set of systems. They are correlated very well with the CH bond length. All right. But so look at the other one. So in this case, the correlation is not good. Okay, so in this case, the correlation is not good. Oops, sorry. Okay, so what we try to conclude from this. So here you see a clear trend between the CH bond distance. Okay, so CH bond distance. What CH bond distance? Equatorial CH bond. That's the most important thing. Okay, so you see a clear trend that is found from the correlation of the interaction energies and CH equatorial bond, but axial bond is not showing a good trend. All right, so that is another observation. So yeah, the another hyperconjugation. So this is called double hyperconjugation, which you can observe in the cation system. Okay, so in the cation system, so cyclohexyl cation. So there are two kinds of interaction. So this is basically an acceptor, sigma acceptor. Okay, so this is sigma acceptor, pi acceptor, whatever it is. Okay, it depends on the the non-bonding orbital. Okay, so this will interact with this. All right, and then so this will interact with this. So there are two kinds of interaction. That's what you see here. Okay, so that's what you see here. Oh, so it is opposite. I'm sorry. So there is a series of interaction. That's why it's called double hyperconjugation. We just named it double hyperconjugation. Okay, so you see a series of interaction. So this is CH and CC interaction, and then CC and the non-bonding orbital having no electrons. Okay, cation, because it is cation. That's a strong acceptor. Okay. So when we analyzed it, so what we found, that's the most important thing. Okay. So when you have equatorial carbocation, the interaction energy is this much. So when we have axial carbocation, the interaction energy is, it's not showing, energy is 66. So which one is greater? So naturally The cyclohexyl cation with the equatorial carbocation stabilizes better than the axial carbocation. So that's what we proved it. So the stability of, you know, CHX, you know, equatorial cation is more stable than, you know, axial cation. Okay. So due to these continuous interactions. So this is a combination of all these interactions. So we calculated the sum of these interaction energies. All right. Yeah, I will delete everything. Yeah, when you look at the correlation diagram, so CC bond is nicely correlated with the population of, you know, CC bond. So because this is the through bond interaction, that's why we use the CC bond. Here CC bond length versus in a relative energies. So you see a nice correlation. Okay, so here you see the group, I mean the period wise how it's been correlated. I'm sorry. So in this case, electronegativity versus population of CC bond, you see a nice correlation by, you know, period by period. Okay, so here it shows the linear correlation. Here it shows, you know, non-linear correlations. Okay, so that's what we observed between CC bond and between, you know, CR bond. Here you see a nice, you know, linear correlation, but it is a non-linear correlation. So why this is happening? Because, you know, CC bond is, you know, adjacent to you know, the cation. Okay, there is a strong interaction. So there is an attractive interaction which is stronger when compared to the CR. So that's the reason. Okay. All right. Okay, so so we use the stereoelectronic effects towards our radical cyclizations. So this is the main aspect of our research. So we discovered a lot of, you know, radical cyclizations. So we started with this one, the indiene system. So indiene, so we use indiene. We generated two different radicals. We computationally designed first and then allowed the experiments to do that. So based on this radical, alpha radical, you can make 5 endocyclization. What do you mean 5 endocyclization? So the bond angle, sorry, the bond cleavage occurs to, okay, bond cleavage occurs towards the ring. So that's what it is. Okay, so look at that. So that is endo. So exo means it is the bond cleavage is towards outside the ring. That's why it's called, you know, exo. So in this case, bond cleavage is outside, it's going outside. So that's why you get exo. So this is endo, 6 endo. So we proposed, okay, oops, sorry. So this is our proposal, right? So this is our proposal, 5 endo, 5 exo, and 6 endo cyclizations are possible from, you know, 2 different radicals. Okay, so alpha radical and beta radical. So these 2 papers are the key papers for designing, you know, a number of you know, radical cyclizations in our group. Okay, until now. Okay, so these interactions totally depend on the stereoelectronic effects, especially this interaction, not this one. Okay, so this is our discovery. So we discovered first 5 endocyclizations. So this was 5 endocyclizations. So that's the work we did. So okay, after Baldwin rules was developed, okay, that is after 4 years. So we discovered 5 endo Dick cyclization. Dick means, you know, diagonal. So that's based on alkyne system only. For alkene, we call it as trigonal. Okay, this is diagonal. All right. Okay, so yeah, this is Baldwin rules, you know, radical cyclization. So we modified the rules. So we modified the Baldwin rules. So this is our discovery. So this is our modified Baldwin rules. Our modified Baldwin rules. This is the Baldwin rules. All right. So this work was published in JACS, and then I didn't involve in the chemical review. They missed me because I was working in different college. All right. It's just for your information. I don't have time to go over everything. Now, if you want, you can go over this review. This is interesting article. So basically, the attack of the radical. What Baldwin suggested? The Baldwin suggested that the radical attack, shows the acute angle, but we showed that it should be obtuse angle. That's the difference. That's the difference. Acute angle attack, obtuse angle attack. That's what we did. Okay. So we proved that. Okay, based on our work, we have designed a lot of polyaromatic hydrocarbons. So this work was done by one of our Indian postdocs. So this is the first work which we succeeded towards 5-exocyclization. So this is another polyion systems to design this halocenes. So this was my second work towards bigger molecule. Okay, towards bigger molecules, we designed another polyaromatic systems. So this work was done by a Maharashtrian guy. I mean, experimentally, it was done by a Maharashtrian guy. Anyway. All right, so conclusions. Let's try to conclude. So now we know how stereoelectronic effects work, how they are useful in organic chemistry. So fundamental thoughtful of stereoelectronic effects actually lead to explore the stability of conformations as well as stereoisomers, by possible, underline that word, that's very important. All possible, I would say all possible orbital interactions, not just one particular orbital interaction. You have to look for each and every orbital interaction. So qualitative designs provided for many stereoelectronic effects. We always talk about some qualitative ideas based on the structure. Organic chemistry needs visual learning. Yes, just by seeing the structure, oh yeah, there is a hyperconjugation, there is an Anomeric effect, there is pi conjugation, blah 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 blah, that we say. But we can quantify all these stereoelectronic effects just by using simple computations. So that's based on natural bond orbitals. Okay, so in not only okay, so in both inter and intramolecular stereoelectronic interactions appearing in the structures can be visualized by various dissected quantities: polarization, electron population, interaction energy, and hybridization. Especially we talk about hybridization, but we can get the right value from NBO. That's the beauty of this NBO calculations. We can get sp2, sp3, sp hybridization from the NBO analysis. Stereoelectronic factors can be applied not only to the design simple molecules, okay, also bigger system, complex systems. Okay, so mainly to develop drug molecules, drug compounds in the pharmaceutical industries. Okay, and then finally, I would like to, sorry. Thank everyone, all my mentors. First of all, I would like to thank our college for providing all facilities to work from home, right? And then my PhD mentor, Professor Venuvanalingam, he is retired now. Then Professor Jemmis, I worked with him at University of Hyderabad. Right now, he's a emeritus professor at IISc Bangalore. He's a Padma Shri person, I guess. He got Padma Shri award 2 years ago. Afterwards, I worked with Paul Geerlings. He's a DFT guy, density functional theory guy. When I was at Brussels, Belgium, I worked with him. Then when I moved to the US, I worked with the Jean-Luc Brothers. He's a computational material chemist. He's he's number one computational material chemist. He has like $50 million projects. You know, he's running with always millions of dollars project. You know, unfortunately, I didn't continue my project with him because that was totally different field. Afterwards, I worked with Paul Schleyer. He was a famous organic chemist around the world in 1980s and 90s. He only discovered the adamantane molecule in organic chemistry. So I worked with him like, you know, like a few months, not a year. Okay, so he just called me and asked me to finish some work. You know, because of Gemmis. Gemmis was the PhD student of Paul Schleyer. That's why. That because of that relationship, you know, I worked with him. Finally, I would thank my postdoc mentor and a research associate mentor, Alabugin. He is even younger than me. You can look at him. So he is six months or 7 months younger to me. So we are like friends. So he was my postdoc boss. So I'm very thankful to him. So I have come up to this level because of, you know, Alabugin. Also, I'm very thankful to, you know, Professor, you know, Jurasti. He's from Mexico. He helped a lot for my, you know, stereoelectronic studies. Finally, you know, I'm very, very thankful to Frank Weinhold. So he's the one, you know, who developed, you know, NBO analysis, you know, NBO theories. Okay. Also, he's one of our collaborators. So he's very friendly. He doesn't show that he's a great guy. He's very, very friendly person. Yeah. Also, you know, they gave, you know, very good reference letters for my green card, everything, like 10 years ago. Oh, sorry, 15 years ago. Yeah. All right. So that's all. Any questions? If you have any questions. Yeah. I'll share my knowledge.
Thank you, sir. It's been a very long and very quiet session, and thank you for your nice presentation also. And people are
Thank you.
appreciating about your presentation, and they are very much interested in the way you presented the concepts, you know. So it is very nice, and thank you very much. And I have taken some questions from the chat box. Maybe we'll move on to that first, and then if somebody is raising their hands, we'll look at it. Dr. Jnanam Selvaraj is asking, how can we analyze stereoelectronic interactions in organic structures?
Stereoelectronic interaction, but what specific interaction? Like what? Like hyperconjugation? Any stereoelectronic interaction?
Dr. Jnanam Selvaraj, if you are online, you can unmute and you can directly connect with Dr. Manoharan. Jnanam Selvaraj, are you there? Maybe he's what? Okay.
Yeah, like I said, yeah, by computer data, you can look at the interaction between the lone pair of oxygen and the adjacent sigma star. Okay, so it'll show you some energy. So that particular energy is due to that interaction, lone pair and the sigma star of that particular bond you anticipate. Likewise, you can go for hyperconjugation too. Hyperconjugation. The hyperconjugative interaction can be, you know, seen from the data. So computed data. It's very simple. Yeah. So basically, I can explain it if you want. Yeah. Just a second. Yeah, just a second. So assume that you. Okay. 1 second. Yeah. Yeah, assume that you develop some molecule that looks like this. Okay, so you develop a molecule that looks like this. Yeah, maybe even aromatic system, it doesn't matter. Okay. So here we have a methyl group, some alkyl group. All right. So this is hydrogen. So instead of this hydrogen, you have some other group. You have some other group, some carbonyl group, some carbonyl group. Okay, some carbonyl group. So how we are going to realize this interaction, this CH bond and this C double bond O interaction? Okay, so do the computations of this molecule and then go to the NBO analysis. So you can look at so this is sigma and pi star or sigma star, both can be obtained. Okay, so sigma, so this is sigma bond. Okay, so this is sigma bond. So overall, this is pi bond. Yes. So this is pi bond. Second bond is pi bond. So you can find out the interaction between sigma, sigma star, and sigma and pi star. Okay, so if you look at the output, so you can pick up the data. So I just showed one example how it looks like. Just a second. Yeah, here it is. This is the output. For example, for the lone pair of oxygen, so that interacts with the sigma star of OH bond. You see that? It's clear. So that energy is 9.15 kilocalories per mole. So that's all. So that is the stereoelectronic effects you anticipate in the structure. Okay, quantitatively you can get the value from the output. This is NBO output. See that this is donor, this is acceptor. See that everything is clear. The Gaussian calculation will give you, not only Gaussian, other quantum mechanical calculation also provides. Is that clear?
Yes, sir. So the next question is, how to calculate the stepwise energies, sir? Is it theoretical or experimental?
Oh, this is all theoretical. This is all theoretical. Experimentally, it can be achieved, but you cannot get the step-by-step energies like computations. Computationally, it can be, anything can be achieved. All right, computationally.
Yes.
Yeah, it's all by computations.
The next question is it possible to apply anomeric effect with all aromatic hydrocarbons?
All aromatic hydrocarbons. Yes, there is a possibility. Yeah, for example, yeah, pyridine, yes. So this is pyridine. So you have a pyridine, the lone pair it's in plane. So this lone pair can interact with this sigma bond, yes, sigma, even though there is a pi bond. So you can achieve, this is lone pair, nitrogen lone pair, okay, nitrogen lone pair. Okay. The interaction between nitrogen lone pair and then carbon, sigma bond, that is sigma star. Okay, so then lone pair of nitrogen and then pi star interaction. So we can obtain, definitely, yeah. That's a good question. So by looking at the stabilizing interaction between the lone pair of this and the pi star on both sides, so collectively you can get some energies. Yeah, that's possible. That's a good idea. But we don't know whether it can be useful to show whether it is aromatic or not. But there is a possibility to show the pi interaction, the pi star, and then pi star, and then this pi and pi star. So there is a pi delocalization. That energy also can be obtained. So anomeric, as far as anomeric effect, so only for the aromatic compounds containing heteroatoms can be used. You understand?
Yeah.
So anomeric effect is applicable only for the aromatic compound that contains heteroatom like nitrogen, oxygen, sulfur. Yes. Anything else? Any questions?
Sir, Krishnamurthy Peryasamy is telling, thank you, sir, for wonderful presentation and fantastic explanation and fantastic approach to explain things. Really great.
Yeah, no problem.
And many people
My
are
pleasure.
saying that it's a knowledge gaining experience and valuable information gained
Right.
from this webinar. And
Okay.
yeah, and I have a question, sir.
Yeah, sure.
Personally, I feel I'm a synthetic chemist, but personally, I feel doing computational chemistry is, a bit harder. We have to visualize orbitals, and that's why
Right.
I missed the chance of doing my project with Professor Venumalingam. Then I moved to
Oh, okay.
synthetic chemist. Because during
I
our
know.
times we have to take lots and we will be go by lots to choose MSc project guide. I
Right,
have
right, right.
I,
So you,
I,
yeah, if
I
you don't have, personal interest, you cannot.
yeah, I was so much interested in synthetic organic chemistry, but one of my friends, she her turn is like she has to go to Professor PV's lab. Then
Okay.
she was a little bit scared about physical chemistry and all other stuff because she doesn't have any mathematical background, and she asked me to swap exchange. And
Okay.
there I had a chance to go to Professor PV's lab, but I refused. And in the first year itself, I had a fear that whether I can do computational chemistry.
Okay.
At that time I felt quantum chemistry is a bit harder, and how can I work with Professor PV? Then and there is a bit hesitance also. How can I visualize orbitals and doing stuff, and I have to play with numbers and related to properties,
Right,
and
right, right.
that was the fear I had, and maybe that is the fear many of us are having. So what is your feeling, what do you want to tell to our PG students if they want to go to computational work with computational chemists?
Right.
What kind of stuff they have to have, or what kind of learning they can adopt if they want to go
Right.
to computational chemistry?
Yeah, there is a possibility to have Spartan program. Spartan program is so cheap. It's only $19 per system, right? So it's available for iPad, iPhone. If you have iPhone, it's useful.
Mm-hmm.
Yeah, you have to have iPhone. That's the problem. So Spartan is very, very simple software. You can model any organic molecules or inorganic molecules and do simple calculations, and at the same time you can visualize the orbital pictures. Yeah, you can see the molecular orbitals,
Okay.
Homo, Lumo, everything. Homo minus one, sorry, Homo, yeah, Homo minus one, Homo minus two, blah blah blah, everything. Lumo plus one, Lumo plus two, all the molecular orbitals can be visualized. Yeah, there is a
Okay.
possibility. Yeah,
Okay. So
the
if
Gaussian
they,
program is very expensive. Gaussian program is very expensive.
yeah, even the workshop is very expensive. We have to pay 25,000 to get trained to work with Gaussian.
Right, right.
Here
You're right.
in some industries, they are conducting some training workshops to learn
Hmm.
Gaussian. So then, without any guidance, can a student of our college or a faculty member from a college of our kind can progress with this freely available software? We need to learn how to interpret, and we have to get into the field. So what is your
Yeah.
suggestion for that?
Yeah, you have to have a special person to design
Mhm.
that procedure first before you give it to students.
Yes, yes.
Like, yeah, that's what I would say. Yeah.
Okay.
So there
Oh,
must be at least one computational chemistry in your college. Yeah.
yeah. Okay. So,
Yeah.
is there any possibility to collaborate with you or with your colleagues, computational chemist colleagues? Uh, because if we have a severe problem with funding. The colleges.
Yeah,
Um,
that's the biggest problem
yeah,
everywhere.
and how much would be the, how expensive would be if we want to work with the computational chemistry projects? Uh, if at
You
all
talk
it is
about
not, if at all,
research.
yes,
Research. Oh, research. It's a zero cost.
okay.
Yeah.
Yeah, that's why I'm little bit curious about getting training and starting research projects in colleges from our region, so that we can make use of our MSc students and we can train them, even though if it is an elementary level. So why
Right.
not?
Right.
Always we struggle for chemicals, and we struggle for funding,
Right.
and
No.
finally we ended up with projects having results which cannot be published anymore.
Yeah.
Our people, they used to do some known things, then they are not able to publish it in UGC approved journals or Scopus Index journals, and they have to go for some bogus predatory journals, and finally their efforts are not recognized well, and then finally
Wow.
they lost interest in research.
Okay. Okay.
That's the past
Maybe I
history.
can give training to your faculty and students for computational chemistry projects.
Oh,
If you have Gaussian program, but
okay, okay, that.
in India in India you can just get it. No, they don't care. Yes, in the US
I
it's very sensitive. In
Oh,
the
I
US
see.
it's very sensitive issue. In
Mm.
India you can have a copy of Gaussian program. They don't care. Do you
Oh,
think?
uh, I don't know who will be, able to share with us. I have
Yeah.
approached some people, but uh, maybe they are having some problem with the institute. If they want to share
Right.
their anyway, I have to approach academic people. I don't have
Mhm.
any industry people, and moreover, they won't forward themselves for free training.
Oh, okay,
Uh,
okay. So
so,
how about big institute? Do they provide any, you
uh,
know, like a computational grants? No, like
no,
IIT Bangalore.
uh, grants
Do
to
they provide?
colleges, to
Yeah, yeah.
colleges.
I mean, only computation grants, computation. You can access their computer.
So far, I don't have any idea about that. I heard
Yeah,
from Rajaram that Rajaram is using computational facility from very big
yeah. Rajaram is
institute.
using different programs. Yeah.
Yeah, and whether I don't know whether we have to go with the proposal, So we are in
Right, right.
elementary level, we are in
Of
a
course,
zero
you have
level,
to go with
and
the
we
proposal.
want to enter into the field. Uh, the driving force for that is nothing but funding. We
Yeah.
cannot, one thing is we don't have proper labs for wet
Uh-huh.
chemistry, and we don't have proper waste disposal things, and we don't have money to
Right,
buy
right.
chemicals to do a very quality research. But we have textbooks, we understand theory, and we can apply our theoretical knowledge, and computational facility to some extent is available in the college. We can make use of
Right,
it.
right.
In India, there is an initiative now called Drug Discovery Hackathon after this COVID-19
Okay.
issues.
Wow. That's great.
They want to collaborate the institutions, the departments, various disciplines, to come up with innovative ideas that can be done computationally first, then that can be taken into industry, or that can be taken into experimental side. So I
Right,
thought of
right.
this, whether why should our brain should go based? We have very good students with very good basic knowledge. Why should
Yeah,
their knowledge should go
I know
waste?
about Saint Xavier's College. Yeah, I used to be you know that I studied in PMT college, Pasamban,
I
Shankaran
not
Kovil.
only mean, yeah, I have
By the
read
time,
in your
I heard
CV.
about it.
I don't mean only our institute, but institute of our kind in the
Right,
rural
right.
area, or any autonomous college or any affiliated college having
Why
a
don't
decent facility to do research.
why don't you guys collaborate? I mean, collaborate with the Saint Joseph's, Loyola College, and get the Gaussian software or Spartan software. I can train you guys overall. Yeah.
Actually, buying software can
It's
be
not a problem.
manageable, but only thing we have to get trained, and we have to to get into the field. Getting
Right, right.
Gaussian is also it can be manageable. It can be manageable, and as you said, this St. Joseph's and Lila guys, they are we are traveling in sailing in a same boat, and they think that we are competitors. And moreover, in the recent MAC accreditation, we have got more scores from than St. Joseph's, and there was a kind of not a healthy kind of comment we
That's
received,
not good.
and they hide something from us, and it is not all the time, but at the time of the announcement of results. So
Okay.
I don't think we can
I got
progress very fast or very quickly
it.
or very effectively if we collaborate with those
Okay.
colleges. So we just want to have a solid foundation, solid platform to grow in
Mhm.
this in the field, if it is possible. So I just want to hear from you what we can think of, what in
Yeah.
what way we can
Mhm.
think of collaborations with any people around the world. That's
Right.
the question.
Yeah, if students have a laptop, that's enough for
Yeah, that's why I'm thinking
two
of it,
computers.
because here each and every student almost they have either smartphone or laptop, and my speculation is from this lockdown time, everyone will be equipped with, all the students will be equipped with a
Laptop.
laptop when they go for higher education.
Right,
uh,
right. Laptop is necessary.
yeah, so
Phone,
why don't we
phone is
use
not there.
that facility, and why don't we use the
Right.
knowledge pool that we have to do something in research,
Mhm.
not in a very big way, just if it is
Yeah.
any corner, any dot in the world.
Right, right. Yeah, if you want, I can train your faculty and students, by Zoom or some other mode. Yeah, that's
Yeah,
fine for me.
that would be
It's very simple.
fantastic. Yeah, that would be
It's
fantastic, and we have to definitely think of it. And I will
yeah.
take your word. It's going to be a blessing to people from this region. I will talk to faculty members of other colleges in South Zone,
Right.
maybe, and
Uh-huh.
I will collect some faculty members
Mhm.
list, and then I will come back to you.
Yeah, I've trained a lot to my students, so here in the US. So everyone is using computations. Most of the experimental chemists, they are using computations.
Oh, I
So
see.
one guy has become a pure computational chemist now from
Oh,
experimental.
I
Yeah,
see.
yeah,
Yeah,
it's
it's
possible.
wonderful. It's wonderful. Knowledge
It's
transfer is always
right.
exciting experience. I
Hmm.
would feel. I
Yeah,
mean that.
starting. I mean, I have to I have to go over like a person who teaches to kindergarten student. That's what
Yeah,
I need to do
yeah.
for you.
That's what we have observed now. That's what we have observed now, and that's the comment we have received also. So
Oh,
very
okay.
very clear, very very fantastic approach you made to explain things, to explain
Right.
concepts in this webinar. After listening
Yeah.
to you when you were talking to Kamaraj College, then I
Uh-huh.
decided I have to host a webinar
Right.
with you and
Okay.
our students, and those who have missed out that webinar should enjoy this. It's been a
Yeah.
pleasure, being with you. And
Yeah, thank you.
thanks
No
a lot for forwarding your helping hand. And definitely, I will think of this collaboration. I mean,
Yeah,
think
sure.
of this
Anytime,
training,
anytime contact.
and I will collect information of interested faculty members and interested research scholars, and I will come back to you. Maybe it will be a small group, but very it will be
Yeah, that's fine. You know, I
effective
can train
learning.
you. Yes.
Yeah,
Yeah.
this that won't be that won't be a very big group. That will be a small group, but only interested candidates will be participating.
Yeah, sure.
Yeah.
Yeah, I have Gaussian software, but it's very old one. Yeah, little
Okay.
old. Yeah.
Okay. Yeah. First, I have to get Gaussian from our
Yeah.
colleagues, from some of our colleagues. Then maybe I will talk to Rajaram about this.
Right, right. Probably
And
Rajaram can provide a software, I think. In
yeah,
India, they don't care.
yeah, I will talk to Rajaram, and definitely I will plan this. Maybe if not in near future, maybe in future.
Mm-hmm.
Yeah.
Yeah, you can manage the computational software with a simple project, very simple project.
Okay.
Like what I have done. You see that we have published,
Yeah.
these works in Jack's paper.
Yeah, exactly. Yeah,
The way in which,
that's the trick we wanted to
right.
learn. And uh, there were many times I regretted not to be in PV's lab, Professor PV's lab, that I missed the chance of doing computational chemistry
Yeah.
projects. And at that time
he's not expert in organic chemistry. I had to teach him
yeah,
what is stereo, what is
actually
stereo.
he was expecting me and my friend Jos Kavita to be in his group, but we refused. That's the bad story, sad story. Then finally,
Good
after
that you did.
entering into synthetic chemistry group and struggling for facilities and spending a long time to establish, and still we are struggling in the colleges. After coming back to colleges, we are struggling for funding and everything. So after this, and there were times we regretted not to be, for not being with Professor PV those days during our MSc project.
But at this moment, you can collect the crystals from different people and do the crystal structure.
Crystal structure we can do. The thing is, we don't have instrument, so we have to depend on any crystalographer to collect the data. And these days the crystallographers, they themselves they solve the structure. Only the refinement, little bit refinement and hydrogen bonding analysis we need to do. So we cannot.
That's the hot field right now.
Yeah, and if we have instruments, and that would be nice. Otherwise, we cannot. That would be a luxurious expectation. We cannot have that. So thank you very much.
No problem. Welcome.
You talk to us with your heart, and it's a fantastic thing that you accepted. First of all,
Oh, no, it's fine.
It's
our student.
It's a lockdown time, and you have your
I'm totally free right now.
Yeah, but
I have no
week
classes.
before you told me you had a examination for your students and you had classes also. So even though you accepted, and it's been a fantastic time we had with you. Thank you very much, sir.
Thank you.
Definitely, I will come back to you.
Sure, anytime. I'll help you.
Thank you.
As much as I can.
Yeah, thank you very much, and my best regards to your family.
Sure. Why not?
Stay safe. And at this moment, I thank all the participants. They were actively participating this one-day seminar right from 9:30 to till now.
I know, from morning to evening.
Yeah, from morning to evening. And just now, half an hour back, they were asking for feedback link, and some people they have already left. And it's been a wonderful experience having a huge participation this
I
time.
saw that hundreds of participants.
Actually there were totally 444 registrations. And some people,
okay.
they have attended some sessions and they missed
left.
some sessions. And for this session, initially we had 150 participants, and now they have already left after filling up the feedback form. And and I have to.
They might be tired.
Yeah. And I have to wholeheartedly thank the head of the department of chemistry, St. Xavier's College, Dr. Jayavins Ruban. He is the person who, initiated this process. He called me one day, Madam, why not we do some seminars or some activities if you can. Then I thought of why not we contact, why not I contact my juniors, seniors, friends, and everyone who are in abroad, and why not we conduct an international webinar, because conducting international seminar would be, very costly for us. So I had a chance of, listening to people who are talking to Kamaraj College. Then I contacted all my friends and junior seniors, and some have accepted, and then I decided to conduct this webinar. So I have to thank thank you, sir. I have to thank Dr. Jayabinsi Ruban for giving me this opportunity to convene this international webinar with his support. He supports me in all possible ways. Thank you, sir. And I have to support the management. They have provided us this Zoom platform to conduct webinars and quizzes and whatever we want to do. For 2 months, they have purchased a package, and there is a dedicated web team to assist us. In fact, they are working, hard. They are involved in multiple jobs, not only conducting webinars, and they are really working hard day and night. Sometimes they, go to sleep at 3 o'clock or 4 o'clock after arranging for the next day's seminar. I have to thank Dr. Lodusamy, our IQC coordinator, and his team members, Mr. Veniston, Mr. Milton, Mr. Sahayam, and Mr. Shankar, and other people who are backing this webinar. Thank you so much, sir, Dr. Lodusamy, sir, and I really thank your team. They have done a wonderful job for us. Always they render their helping hand whenever we just give a shout. And I thank all the faculty members of Department of Chemistry. They were actively supporting conduct this international webinar. Today we have Industry Academia Interaction Meet. For that also, they are working for us in the background. Thank you so much, dear colleagues, and thanks a lot for being with us. Thank you so much, and definitely we'll be in touch with you. And it's a great honor. We feel like, we are connected with people like you and high profile people like you. Thank you very much. And
No problem.
yeah, it's a boon to our students also. And it's a gift to them. And I thank God Almighty for making this day a fruitful one. Thank you so much, everyone. Thank you for all your feedback. And we'll meet tomorrow in Industry Academia Interaction Meet.
All right. Thank you.
Thank you, sir.
See you.
Thank you for all your feedback. And we'll meet tomorrow in Industry Academia Interaction Meet.
Thank you. Thank you.